Hello. How are you guys doing? Am I a quick round of voice check? You guys can hear me, right? Can I get a quick confirmation? Awesome, awesome. So it's about 8. I think without further ado, we should start. And what we did yesterday, I will share my screen in a minute. But before that, uh, can any one of you wants to put what did we do finish yesterday? Till what time did we till what part we actually finished our topic? We understood what was, what's what is neural network and what is the core tenets or the foundational pieces of neural network. We actually try to build a very basic neural network on our own, and we saw that it's, conceptually at a at a foundation level, it's not that difficult to understand what it's trying to do. If we are trying to figure it out still, that how different it is from the traditional machine learning algorithm that we are aware of, right? Isn't it? And we found out that one of the things that is very clear is that this is a non-parametric function. And what do you mean by non-parametric function? Do you remember what we discussed yesterday? What is non-parametric function? How do you how do you define something as a non-parametric function? Anyone? A non-parametric function is a type of a learning algorithm which doesn't have, it's not a line, but more than that, it can be more than that, it doesn't have a function definition yet, right? For for any other learning algorithm, we use the definition already. Linear, it has a mathematical form. We are not sure. We have not given the mathematical form before we solve the problem. We have not chosen it from a bouquet of list, right? For linear regression, what we did, we chose that we will do use a hyperplanar line equation to segregate, right? So we already chosen. So in case of non-parametric equations, we don't choose, and we will actually see that. So we also gone through this. The class is started. I'm going to share it. Okay, we are just discussing. I have not shared anything, so the class is actually started. We are just deciding. We're just discussing what we completed yesterday, so that it is fresh in our mind, isn't it? So we've also seen what is a core network, right? Remember what we've also seen that what is a what's a neuron, right? Neuron has two operations. Remember? Do we remember what are the two operations one neuron does? Very important for us to understand. What are the two basic operations that a neuron does? Two very fundamental operations a neuron does, an artificial neuron does. Anyone? That is correct. First is an aggregation, multiplication with weights. First is an aggregation operation. That aggregation operation is nothing but summation. Perfect. Yeah, it's going to sum something, weights with the inputs, and then it will add a bias as well. And then the last one is a non-linear function, which is commonly known as activation functions, right? Can we know? Can you tell me what is an activation function that we all have used earlier in traditional machine learning? Yeah, sigmoid. Softmax is also a activation function, but softmax has a very special place in our heart. Okay, and I will actually show why softmax being an activation function might not be a good, thing in the middle of the layers. We have also understood that there is something called as the middle of the layer, and those kind of layers are called as, what do we call those middle layers? They have a special name, right? They are called as hidden layers. Why do we call them hidden layers? What is the intuition behind calling them hidden layers? What is their core objective? We will look at that today. They are called as hidden because their objective is to, they are not, they are sort of, they are exposed in a sense that they are hidden, they are exposed. But the thing is that that's also true. They are overall, what they do is not very clear. But the point is that, they are the one who actually they are the one who are actually trying to extract some features, right? On that, neural networks, what is the core difference between machine learning and neural network? Apart from everything else, what is that one thing that's making neural network a neural network? It does feature engineering on its own. Yes, most of the feature engineering happens in that neural network. It can build some really complicated features, which is very difficult for a human beings to generate, right? That was one of the key thing, and we will see that, right? And we've reached to a point. Where did we reach? Where did we ended yesterday? Do we remember? We were discussing something. We discussed that we had a. I'm still not share the screen. Let me share it actually. Maybe that will be easier. Okay. And okay. So let's. You can see. You all can see my screen, I assume, right? Let me just open the chat window also in case people respond. Yeah. Right. Okay. So this was the neural network that we discussed. Remember, right? We had lots of inputs. These are called as input layers, and we had some output layer. Right. Each of them has two parts of the problem. They do summation and then do some sort of non-linear activation function. Right. This is what we did. Right. This is exactly same thing that we did here as well. Right. Let's go to any of our network. Yeah, so this is what was happening here as well, right? So, and right, okay. We've also looked at one of the very early network. Remember what was earliest network that we have, which sort of resembles neural network? What was the algorithm that we saw? Do we remember? Perceptron. And perceptron, does it have any linear? Does it have any activation function? It had a very basic activation function, right? But it was almost linear. And the problem with perceptron, it was only one layer, right? The perceptron system had only one layer, right? And we left it a place. We said that something happens, like the way we've also gone through this part. Where let me also share the slides. Just a sec, right? And let me actually do this and right, okay, I hope you are able to see my screen, right? So we saw that there is something called as feed forward network, right? So let's just go to this. So we saw that there is something called as networks which goes in front, right? There's a forward pass and there is also a backward pass, right? We have gone through that basic tenets of a core neural network class that we built, and if you remember, we have added a forward pass and a backward pass, right? And that is where we sort of left for the day yesterday, and we said that we will come back and look at this. We will come back and look at this backward propagation a little bit closer, right? Are we all in same page? Are we all in same page? Right. Awesome. So what we're going to do is something that rather than going through the slides, I'm going to take you to a little bit of whiteboarding. I just happened to manage it before the class. I hope it helps. So what we will do is, like, given this class, so our problem is this. Okay, this is a problem statement that has been given to us, and what we will do is, like, we will unravel each aspects of this particular neural network, and we'll try to understand what is happening and why it is happening from a very intuition point of view. Okay, I would love to finish this lesson before our break time for sure, including 2 practice labs. So this will be a little intense. Keep on asking questions, okay? And I will also love to in our second break. What we will do is, like, we will start our next lesson as well, right? So let's come back to this problem. The problem is very simple. Like, given my 4 x's, which is my features, I am to create a neural network which can actually which can actually predict. I will figure it. This is you can always see the recording. Yeah, I can share it. It's fine. What I'll do is, like, I will talk to the LSM and I will figure out a way. I haven't yet figured out a way how can I share this thing. This is something that I just created. Okay. If you want it, I can give it. It's not a problem. The purpose of me creating this is that sometimes, it's easier to go via pictures than mathematical equations for everyone's benefit. So that's the reason I've created the picture, but I will try to see if this can be shared. This is mine, so it's
Hi,
not a problem.
Sandeepan.
Yeah,
So, if you want any file to be shared with the learners,
yeah,
please email me so that I will
yeah,
be
I will
sharing
do
with
that.
the.
Yeah, I will.
Okay, thank you so much.
Okay. So what we will do is this. Okay. What we will do is this. What is our problem statement? That given this input layer, sorry, given these features, we have four features. We have to predict whether x1, and this is a supervised learning problem. We already know the historical. So we know this x1 is of class 1, x2 is of class 2, x3 is also in class 2, and s4 is class 1, right? So the problem statement is very clear. This is a supervised learning problem. We have been tasked to create a neural network, right? And for some reason, we will not dwell on the fact that why we have chosen three hidden layers. For some reason, let's consider the fact that our manager has said, right? Manager has said that please choose three layers and each layer should have three neurons. Okay? And we will not question him for now, and we will question him later when we do hyperparameter tuning. But for now, we will think that that's what he wants and that's what we will do. So this is my network diagram, right? I have four features and I call them as input layer, and I have four, three hidden layers, right? The first one is this, the second one is this, third one is this, right? This is my first one, right? This is my second one, this is my third one, right? In fact, this is also my fourth one, right? This is no more a hidden layer, this is also called as an output layer. And if this is my output layer, then it's going to give us probability, because this is a classification problem. Till now we are okay with this? Are we okay with this? Since this is a classification problem, the output layer will actually give me what it will give me. It will give me probabilities, right? Not a continuous number. We are okay with this from till now? Perfect. So we also looked into the fact that the first pass, the direction from left to right, from our features to our classes, is called as a forward pass. If you remember, we have actually implemented this, right? The forward pass. And there is also, so neural network on its own is not only forward pass, it also does backward pass, which is called as backward propagation. Okay. Is there no audio, guys? Can you guys give a shout out? Is audio is fine? Can you all hear me? Someone, okay, you can hear. Okay. How can you know how much hidden layer? We said that, right? For now, our manager has said, and we will accept it. However, the real answer is that we will do hyperparameter tuning. Okay, and we'll come back to that at the right point. So now to train this network, what do we have to do? What do you mean by training this network? And let's try to unravel this. Okay, so I have written down what do we have to do, and given the fact that we know that what are the core fundamentals of building a network. Remember, we have built a class called as NN. So one thing is clear, the first objective is to create an object or a holder, right? Are you guys familiar with this concept called as object or an holder? If you are from OOPS or object oriented background, we know, right? You know that I need to put things in somewhere, right? So this NN is nothing but that object, right? And each of this will have some significance when we go to higher order frameworks like TensorFlow, Keras, and TFLearn, okay? So we our PyTorch for that matter. So what we will do is like we will create that NN class. We have created that NN class. If you remember, there was an NN class that we did, right? And we've created an object of it. Now it's very clear that we had, how many layers we had? We had 1 layer, 2 layer, 3 layer, 4 layer, isn't it? So we need to add 4 layers, right? And let's add 1 layer at a time. So let's add 1 layer, and we will say that when you add the layer, please add 3 neurons. And in this case, we will choose the activation function as, let's choose some activation function called as ReLU. ReLU is one of the most simplest activation function. Formula wise also it looks very simple. It basically says that max of 0 or the actual value. That's all it is. Even if you're sigmoid, if you see, right, formula wise it's actually pretty complicated, right? 1 divided by 1 minus e to the power of minus x, right? Looks complicated. But ReLU is simple in the sense that it's either 0 or anything which is not 0. So choose the value which is maximum of 0 or not, right? So we'll choose ReLU for now, okay? So how we will generally write something? This is how we'll write, right? The way we'll write, these are all pseudocode, okay? I just wanted to give you a sense of things, that how things happen. So we will say that add a layer, assuming the fact there is an add layer function in my NN class, add a layer, and then when you add it, always there are two parts to it. I'll add a linear layer, right, which has my three inputs, and basically three hidden nodes. Essentially, hidden nodes means three neurons. This value of hidden nodes will be 3 for my first layer, and my input dimension is going to be 4 in this case, isn't it? And I'm going to add an activation. I said that for my this particular layer, I will choose an activation function ReLU. Okay, this is clear. I will repeat the same process. So I will name this layer as H1. Okay, and this is how I add a layer in my neural network object. Okay, and this object is just nothing but a placeholder. I will do the same thing for H2. Okay, I have added a layer. Okay, and I said that for that particular layer also the activation function is ReLU, and I will add one more layer, and I will say that for that particular function, my activation for that particular layer H3, my activation function will remain ReLU. So these three are my hidden layers, right? That's one thing is very clear. However, I have to add one more layer. Now the thing is that this last layer is a little special. So I've added this layer, so I will use the same function. I will add this layer with, of course, a linear layer, right? The linear part, the summation part is always linear, right? And the activation function, I cannot use ReLU here, okay? For any last layer for a classification, I have to use a function which gives me value between, what should I use a function with in the last classification layer? This has to produce, yes, 0 or 1. No, it should be between 0 and 1. I need probabilities, and not only that, I need probabilities. Remember, I need probabilities output, right? A classification is generally a probability output. So the values output of here, this should be probability output. So I have to use the activation function as softmax. You know what softmax does? Softmax has this nice property which actually all these things, what it will do is like it will create probabilities in such a way that addition of all this number will be equal to 1, right? So probability of class 1 plus probability of class 2 will be always 1, okay, right? So that is what softmax does. Softmax given a list of all classes, and since there are two classes, my output neuron will always be 2. Yes, so we will choose that. How do we know how to choose the activation function? We will actually discuss that. Don't worry. Okay, we have a specific discussion on that. We will go through how do we choose activation function. We will also go through how do we choose loss function and so on and so forth. Okay, we will discuss that. Now for right now, let's assume that we are trying to still understand the neural network, how it operates. Okay, like what will it happen? So just let's focus on that first. So if you are clear on this part, then one thing that we understood is that the last layer is special, right? Last layer I cannot use ReLU because I need the probability output. I need the probability output in such a way so that my probability distribution across all my classes in summation should be 1. It cannot be greater than 1. Then it basically breaks my probability principle, right? So essentially it will say that class 1 might have 0.75 and class 2 might be, then in that case can only be 1 minus 0.75, which is 0.25, right? Something like that. And softmax, by just adding softmax here, it very nicely handles that part. Okay, so that is one thing. So now when you give this network to train, so this is a network that you have built. Clear? This is done. Now we have 4 layers, 3 hidden, 1 output. Your basic tenets of the thing is done, but now you have to give it to training, right? By definition, just adding it into a neural network object, it will not train on its own. You need to literally trigger .fit, .train function, right? So how does a typically .train or .fit function looks like? In this case, it's .train function. Okay. So what it look like is that it will call a function called as forward. Okay. What does it mean? That it will, that for every layer I will have to do a forward pass. Forward pass. Okay. Right. So why should we use softmax? Softmax, essentially the difference, softmax is this. Okay. Softmax, what it does is that Softmax gives a range between 0 to 1, not 0 and 1, okay? It will always give you a value between 0 to 1, and in the last layer we have, our objective was, it's a probability output, and if you add all the values, all the outputs of this particular operation, it will be equal to 1. Hence, it's very nice way to represent probability. Softmax gives you that ability. Hence, for any classification problem, our last class generally will be softmax. Sorry, last activation function on your last output layer will be softmax, right? There seems to be a problem with Malathi. Can LSM help here? Yeah. Okay, so what do we do in the train process? Please, let's focus on this. We need to do a forward pass. We will do that. Can you guys the difference? We will do that. We'll come back to this, okay? Sigmoid versus softmax is an activation function. We will come back to that, okay? Today only we will discuss about all those things. Focus right now on the tenets of the neural network, okay? That this is what is happening. We have to, okay? Let's focus on that first. So we'll have to do a forward pass, and once we do a forward pass, we have to compute the loss, isn't it? And once we compute the loss, something else we have to do. We have to go back and do, what happens is we have to go back and update all these weights. These lines indicates what? These lines are nothing but weights, right? We have to go back and update these weights and then apply the weights. We have to change the weights, right? We have to first find out what is the difference of loss and then what will be the weights, right? And then basically apply the weights. So on a very high level, on a very intuitive way, these are the 3-4 steps that it happens in a train process. You do a forward pass. Forward pass is nothing but this function, okay? This is exactly the function, basically summation and activation, right? And you do for every such layer, for every such neuron, go to the last of it, compute the loss, come back, compute the gradients or the change in W's against that particular loss, and then apply the weights. This is how basically apply the change in weights. This is what happens in train process. Are we clear till now? Before we actually take this to a next level, okay? Okay, awesome. Now let's do one thing. Let us exactly see this in a very graphical way, okay? Let's look at how does forward pass looks like, okay? I'm just depicting in a way so that we can all understand it without much. So now one thing is very clear. This is my x1, x2, isn't it? This is my x1, x2. This input is clear to you. If you think from a matrix point of view, this is a matrix of features, right? Where I have given a list of all my features, right? I have given it one sample, right? I have to give one sample at a time, isn't it? One row of the training data set at a time, isn't it? If there are n samples, I need to do this n times. So suppose this is my 0th index of my panda data frame, and I have inverted and made it a column. This is clear to you guys? Like I have given a matrix of x1, x2, x3, x4. These are all features. Okay. Now I have called. So first is this is my input. Remember, first is my hidden layer was actually an aggregation function, this is my aggregation function, right? W dot x plus b, which is wrapped into the ReLU function. Do you understand this nomenclature? Are you able to understand? Can I represent my hidden layer like this? Can I represent my hidden layer like this? ReLU is nothing but a function, and in that function I have given that summation, right? So this will give me exactly one output. I will come back to that. Why there are, okay, I will come back to that. What is W12? I will come back to that. But do you understand this notation now? Okay, that I have some summation and then on top of that I am doing an activation. Right. Now let's discuss that what we said is that my first layer has 3 neurons and my input layer has 4 neurons. So how many weights are we talking about? How many weights are we talking about? Just let's talk about weights. Yeah, so there are 12 weights. Clear? How many biases will be there? There will be actually 3 biases, right? So essentially there will be actually 3 biases, isn't it? If you put a 1 here, it will be 3 biases. So that's the reason this particular layer, this particular first layer will take how many weights? 12 weights. So this computation W is nothing but W, this value, okay? There are 12 weights that you have to multiply with 4 such inputs and 3 such biases. I am just generalized it. Are you able to understand that? Awesome. Good. So now this operation will give me something, right? So now this operation will give me an output. What will be my output? What will be an output of this operation? What will be the shape of the output? It's very clear, right? 3 neurons will give you 3 values. Each neuron will give you one value each, right? Each neuron will give you one value each, right? So this is my output of H1. So H1X1, H1X2, and H1X3. Yes, we have 3 biases. I have just not represented bias, okay, I was just got tired of it. But the thing is that there are actually 3 biases. You are right. There will be that many number of biases as you have that many number of neurons, right? Isn't it? So let's consider that there is only one bias for now. Okay, just move on with it. Consider that we have no bias for now. But for generically, I've just added it, right? Now the output of the H1 layer is this. This is clear, right? Is this clear that output of H1 layer is this? So now I have actually transformed my input X1, X2, X3, X4 to HX1, HX2, HX3. What do you call this operation? Do you think what is happening here? We just did feature engineering, right? You have transformed your original data frame or original data by some sort of function to a completely different new data frame, right? This is a new you did dot product. Not only that, you did dot product plus an addition operation, and then you did ReLU as well, na? ReLU is a non-activation, it's an activation function, right? What does ReLU says? That if you have a 0 or 1, then it choose 1. If you have 0 or 0.25, then choose 0.25. Whichever is maximum of zeros, choose this one. So the value here, the summation operation is 0, then it will choose 0. If the summation operation is greater than 0, then it will choose that value. So at the end, this might be 0, 1, 3, whatever it is, right? Based on whatever you have given. But the point what I'm trying to say is that this operation of ReLU and the aggregation has created me new features. Output of my layer has given me a sort of totally new input. This can be considered as a feature, right? You understood? Is that part clear? That you have did a transformation. It's like there are not four outputs. How many outputs will be there per this thing? There were 4 inputs, but we had only 3 neurons, right? In my H1 layer, I have only 3 neurons. So 1 neuron will give me 1 output, right? Yes. So basically it's fine, right? I can have n number of outputs and n number of inputs. Yes, correct. Right. So that's clear, I guess. So now what happens? So now the most important point I'm trying to say is that you have just transformed your actual data point to something else via this logic, okay, this hidden layer logic, ReLU of some summation activity, right? A nonlinear of some summation activity, right? And we will continue. We are just on the first layer itself. Then one thing is very clear. So the output of H1 will now go to output of H2. Look at this thing. The output of H1 will go to, this is H1, right? This will now go to H2. So we have 3 inputs and then 3 outputs. So how many weights are we talking about? We have 9 weights, right? And of course that many number of biases. I just assume that there is one bias, okay? It's just easy to ignore bias, but don't ignore bias. Actually, biases are never ignored, okay? They are also treated as same as weights. So now I have this W9, and I'm going to do the same thing. This W9 is nothing but this, okay? So I'm going to, again, my second layer is also an activation function of ReLU. So again, the same activation function of ReLU, but now with this. Now my input of H1X1 again gets changed into H2X1, H2X2, H2X3, right? I have started with X1, X2. I have already done my second transformation. Every time my input goes to my layer, this simple function is activated, and I get a different data point altogether. Clear? This is nothing, what do you call? This is nothing but feature engineering, right? Sorry, this is nothing but feature extraction. This is, if you use a polynomial feature extraction, what do you do? This is what you do. You add some weird logic or some known logic or weird logic, and then the number that you generate has very little human sense. Right? If you use this class called as in sklearn has a class called as polynomial feature generation, right? So that's what it does, right? It will take a big number and then it will generate it, right? Yes, of course, output of previous layers will always become input to the next layer, right? And this is clearly stated in this diagram, right? This diagram is this self-explanatory. This diagram states that whatever is my output of previous layer will always go to my next layer, right? Okay. So I will do this for H2 itself. I have got a new output, and I have got 9 things. I will do again for my. I have one more. I have actually 2 more layers. So what happens? I will do the same thing. So now H2 X1. Yeah, shoot, no problem. Just type. I will try to answer it. Okay. So H2 X1, H2 X2, and H2 X3 goes via one more transformation on for the hidden layer 3, and the transformation remains same. So we have the same. We have again 9 new weights. How to calculate bias? Biases are okay. How do we calculate bias or weight? Anyone? How did we start with what value of W or what value of B? Anyone? We've discussed this yesterday as well. If you remember, we start randomly. Yes, we will start randomly, and we will see that we don't calculate. Your model must learn the weights and biases, and we will see how and why. Why it is so important. Okay, we will spend on this as much as possible, and let's get this understanding very clear. Who creates who? You as a machine learning engineer or the model creator should not assign anything to the weights. You only assign the first weight, and that's an initialization parameter. You randomly assign them, and then as the model trains, it improves the weights, and we will see why. Okay, and that's a good question. So now we are at H3. Again, we find out that our input of hidden layer was 3, and output of hidden layer also is 3. So which means I need actually 9 weights and so many biases, right? So I will do one more ReLU operation because that's what we have chosen. You can choose some other activation function, not a problem. But in this case, I have chosen ReLU, right? So I have got a new output, H3X1, H3X2, H3X3. This is my third transformation from my third layer. Now I have reached to a layer, which is my output layer, right? If you just go back to my output layer, right? This looks exactly the same. Only thing is that since this is an output layer, there is no more ReLU. But I know that softmax is also an activation function. Okay, so I will wrap this as softmax, and then but inside this I will actually add. So this W is nothing but this 6 waves that I am talking about. Why 6? Because for this particular last layer I have 3 inputs and I have only 2 class to support. So it's going to be 3 into 6 weights and that many number of biases, right? Are we able to understand this? That how now from X1, now if you actually see, this was my original data. This is something that we can never change. This we are given, right? How can you change this? We can't change this, right? This is what we have. From here we do one transformation, second transformation. These are nothing but transformations and feature extraction. Third transformation, and after the third transformation, we get an output of H1, X2. And since this is a softmax function, this is a probability output. And we know that all the values of this particular matrix add up to 1. And they can be treated as a probability value, right? So this is what a forward pass is all about. And we are still not done till we are the last point. But till now, are you able to understand what is the role of each layer is playing here? Are we able to understand what role a layer is playing here? Right. So after the output, what do we do? Anyone? Before I scroll to the left side or right side? We have got the output. This is my class, right? This is the class probability of, I have 2 classes. This is class 1, class 2, right? I have my class probabilities here. Softmax has given me. Yeah, so how does it compute? So if you actually, we can look at softmax. So what it does is that softmax is nothing but, suppose you have a number, you have, 1 comma 2 comma 5, right? And if you pass this via softmax, right, what it will do is like, it will first scale it between 0 and 1, okay? And it will say that in this scale, where is 1 represents, in this scale, what is the probability of 2, where 2 represents, and in this scale, what is 5. Hence, it basically puts in under a measure of 0 and 1, and that becomes the probability value. We can go to the equation of softmax in a bit, right? But this is what happens. You understand the intuition about it, right? You understood the intuition about it, right? So you can have any number of values and you can project it between a 0 and 1 values, right? That's what you are trying to do, right? So and that's nothing but that is what we can consider as a probability. So in this case, what will happen is that 5 is high, which means 5 has a higher probability to become 1. Will have a very high probability. This might be 0.85, and this might be like 0.1, and this might be 0.001, something like that. Okay, we will look at that. We will look at softmax very clearly. Okay, remember this point. We have a lot of opportunity to come back. But for now, let's just understand that softmax does this beautiful thing for us. Okay, and don't worry. We'll have to look at this very carefully. So now, what is the last thing that we have to do? Given that we have got the probabilities out of it, we're still not done. There's one final thing. Yes, we need to compute our losses. Remember, we have done xtrain. This is my xtrains, one of the xtrains, right? This is just one sample. And what we'll do is like, we'll present this probability to my loss function. Loss function is, what is the name? Take any loss function. We will actually, right now we don't worry about what loss function is, but this is what we'll present to my loss function. At this moment, all my loss function is care about is output of my last layer. It's nothing but this matrix it will care about the probability of all the classes and my y true. Y true is always coming from my data set. What will be typically my y true? What will be typically my y true in a matrix form? It will always be either 0 or 1 or 1 or 0, isn't it? Because either one of the class is always present. Both will not be present, right? Either one of the class will be present. In this case, it says that the class 1 is not there, but class 2 is there. In this case, class 1 is there or class 2 is not there. So, and in H4x1 and H4x2 is nothing but some probability value. Loss will do its loss computation across all such samples. We are not talking about all samples, across this particular sample. Right? I have given us very specific sample and it will compute a scalar value. It will say that for this particular sample, I have got, how much I have got? I have probably got 0.29 loss. It's a scalar value, isn't it? For that particular sample. This is the whole game of forward pass. Guys, are we able to understand what happened in forward pass? I have computed per layer wise those two operations, and I computed the loss, and I have got a loss value as well, right? For that particular example, right? Clear? Now let's look at few of the things. Is it clear, guys? What's the loss value? Loss value will always be some. I just randomly put 0.29. So how will you compute the loss value? Essentially, minus this with the actual output of this. It's not exactly a minus. Depends on what loss function will you use. Yeah. So y true is so output of H1 is nothing but my prediction, right? This is my prediction, right? Output of H1 is the probability of classes. This is my prediction. This is my y pred, right? This is my y prediction, and I already have my y true. So I will simply pass those to the loss function. Loss function only cares about those two things. It doesn't matter anything else, right? And you can use any of the loss functions, cross entropy, binary cross entropy, or in this case, this is a one class problem, so it's going to be binary entropy, binary cross entropy, and it will compute some value. That value will be 0.29. I'm just saying, okay, can be anything, right? But it is a 0.29 for one particular sample, guys, right? And it has to do this for all other samples. Clear? Is that clear to us now till this point? Let us know if this is clear. This is clear, right? Can I get a shout out of this is clear or not? I'm going to complicate things a little bit more, okay? And I want to complicate things. So now let's ask ourselves, what is the structure of this learning function? We've talked about so much about parametric and non-parametric and so on and so forth. Can I say something like this, that my learning function actually is this equation, right? This is the equation of my learning function, right? This is almost same as if you had your y underscore pred equals to mx plus, sorry, in this case we have how many, m1 x1 plus, you know, m2 x2 plus m3 x3. Are we able to appreciate what we are doing here? X4 plus c, right? No, that's fine. So don't try to remember again. If you try to remember, you'll overfit yourself. Okay. So try to understand it. But the thing is that this comes in layers. The more you approach it, it will come in layer. And of course, you can always go back to recording and try to other sources. But don't try to remember. If you try to remember, what will you become? You will overfit yourself. Okay. Don't try to overfit yourself. Okay. Ask questions, and we can actually try to understand what's happening. Just trying to mug it. Okay. Now, if you have to solve this problem using a linear regression or logistical regression, the core problem will be this, right? M1 x1. The core parametric function will be M1 x1 plus M2 x2 plus M3 of x3 plus M4 x plus c, right? Do you understand what I did? We had four inputs, right? Guys, we had four inputs here, right? So if you are going to use linear regression or logistic regression in this case, so your equation will be like this, right? You will have four coefficients and one c. On four dimension, you're trying to draw the hyperplane. Remember machine learning basics, right? So that is the difference. Clear, right, guys? If you're not clear, just let me know. I'll explain one more time. This is important. Yeah. So in this case, if you have been told that you solve this using logistic regression, yeah, good. So if I give you this data set and I give you that I have to predict two classes and I ask you to solve with logistic regression, you already know that the equation of the function will be in this form, isn't it? Because since there are four features, I will have four coefficient of each of the features and then there will be an intercept, right? But we did not use logistic regression, we used a neural network and we didn't know the function. So now you look at it, if you look at the function's form, what will be the structure of the function form? The function form will be something like this, right? Ypred, we can also call it as f of x or f of x of w, in this case that a function of x or function of x of w, function of x given my weights is a function of softmax, then another function which is this one, then another function, then another function, like is nothing but a function of a function of a function of a function. It can also be represented like this, right? Do you understand what happened here? Exactly, right? So that's what we did, right? If you have to express all of them in one function, internally what happens? A neural network is generally represented like this. It's basically a function, under this a function of a function of a function of some value, right? Right? So in a very generic manner, what happens is that you know ypred or a value or a function of a neural network is something like this. You can express like function of a function of a function of a x or some sort of x, okay? But it will never be x. In this case, it will always be a function of w, right? So now you understood, right? Now it's clear. Is that clear? It's complicated. It's a little complicated. Now this is what the maths behind it. This is what the maths looks like. If you're going to understand the math, this is how it will look like, right? And if you see, right, the only variable in this whole equation, what is the only variable in this whole equation? This equation, what is the only variable? What is the thing that you can change? No, can you change x? Okay, guys, can you change this x? I'm talking about this. Can you change this x? Why can't you change this x? Why can't you change this x? Correct, because x is the input. You can't change it, right? It's something that, so the only thing that we can change is nothing but this w and b. How many w's? 6w here, 9 here, 9 here, 12 here, and there may be 3w, 3b here, 3b here, 3b here, 4b here. I have taken only 1b, but essentially all we can change is weights and biases. And if you have to generically say, that's the reason it's all about weights and biases. Your prediction, your function is nothing but everything about those w's that you choose and those b's that you do. That's it, nothing else, right? That is the reason. Okay, is that clear? If this is clear, let's complicate a little bit more. Okay, guys, the machine learning algorithm does not look, still it's not complete, right? Now, what we also call as machine learning as a optimization problem, isn't it? It's optimize something. What does it optimize? It optimizes a loss function. Its objective is what? We remember we have used this loss function at the last. Now I have computed this loss 0.029. Now let's come back to this loss function. Okay. So what is the loss function? Each example's loss function is that if some loss function, whatever loss function algorithm that you use, if you pass it y true and y pred, it will give you a number for each example. So the whole loss of the whole model will be that you have to average it out, right? For compute loss for each of the example, each of the sample, if you have a million samples, for each of the samples, you need to compute your loss because you will get one y pred and one y true, isn't it? And then you have to divide by n. Clear? Is that clear? Now, if you actually, is that clear? Right. So now if we actually expand this particular loss function, we know what is y pred. Y pred is nothing but this equation, right? What is y pred? Y pred is nothing but this equation. Hence, my loss function looks a little bit like this, isn't it? Is it too complicated? It's not too complicated. I'm just replacing. I'm just trying to tell you that the mathematics of it is seen like this. That it is actually everything is a function. So loss is nothing but this is individual sample loss, that y true is given to you, and this is my y pred function. This is my y pred function, and this itself is also a loss, is also a differentiable function, right? Cross entropy is also a differential function. So now one thing is very clear from this statement. Loss only depends on what then? If this is what we depend on, can we change y true? We said that we cannot change x true, x. Can we change y true? We can change y true? No, we can never change y true. It's part of my data set itself. So, continuing our same idea that it's a function of w, you can say like this, that loss only depends on w and b's, right? This is the only reason why. What is this value of 0.29 that we got? Because for some reason, why we got 0.29? Because whatever w and b we have chosen has given us this 0.29, right? So the other words, loss is nothing but function of w, weights and biases, right? Nothing else. So the mathematics behind it looks like this in this angle. Now then what is our objective? Our objective is that we have to reduce loss. Oh, 0.29 is not good. I have to go to 0.15. No, not as close to 0. Now, right, our objective is to go to as close to 0. That's what it is. So now the question comes back to that, how do we ensure that loss goes to 0 in such a way, right? The only way we can change is w's and b's. So we need to use at this point this equation of differentiation, that how much change of w that we should do so that loss should go towards 0. This is my differential equation. Clear? That is the reason why we actually try to compute dl by dw. Like different, this is the partial derivative, right? It will become partial because it's, yes, so basically dl by the rate of change of how much change should I make in my w. Okay, how much change should I make in my w so that it will change L by certain amount. It has to go down. My L has to go down. And this is a very clear-cut mathematical problem of partial derivative and derivative. It's a differential equation problem, right? And how do we solve this? If you have to solve a differential equation like this, no, we don't solve. Learning rate is somewhere else, not here. Learning rate will come back. Well, I'll come back to you, okay? But how do we solve this? The way we solve this equation is not a simple equation, okay? We have to solve this using a rule called as chain rule, okay? What does chain rule says that if you have partial derivatives to solve, so if you have to solve this equation of a function of a composite function, essentially these are called as, this is called as a composite function. I am trying to do a derivation of composite function, right? I'm trying to compute derivative of a composite function. This is my loss function, right? In some form. So if I have to compute, my chain rule says that I need to, I need to find out gradients and I need to build partial derivatives of each of them, right? And once I can find, derivatives of each of them, then only I'll be able to compute this dl by dt. So basically, if I have a function like f of g of x, f of g of h of x, then I need to, and you need to know, right, if what is the derivative of d of f by d of x. So it's gonna be d of g into multiplied by d of g divided by d of h, and then d of h divided by d of s. In our case, since we are trying to compute d of L by d of W, this will be, so how many functions that we have? Remember how many functions we have? Let's see how many functions we have. We seems to have one function. We seems to have two functions. How, basically one, two, three, basically four functions. No, in fact, if you add loss, then it will become five functions, right? So if you add the loss, it will become five functions. If you add regularization, it might become six functions, right? So that depends on what are the things that we'll do. So, but essentially what it will become is that this will become a six function derivative. And who does this? What are we trying to do here? We are trying to find out what is my W's change should be to reduce my loss, right? Change of W, how much should I change W? How much change should I do in each of the W? By the way, when I say W, each of the W, by the way, all the W's that I have here, 6 plus 9 plus 9 plus 12, all the W's that I have here. This is 18, 30, 36 W's that I have, and so many biases, right? So how many change I should do in each of the W's to actually overall change my loss? This is chain rule, and this is what backpropagation uses. This is how backpropagation uses. There is some more mathematical constructs. D of g is just trying to show you d of g is nothing but this function. Okay, like I need to find out differentiation of d of to x, right? So this is g is nothing but the function. I did not wanted to write that big thing again. So that is what I'm trying to say. If I have four, we said that we have four functions. I just took I took four functions actually. D of L, 2, 3, 4. Actually, there might be five functions, right? So that's what I use. So, but this is chain rule. This is exactly what happens in backprop. What we did essentially is that we computed for every weight how much change I should do. That's all backpropagation does. And backpropagation happens from here. Once you compute the loss, backpropagation will kickstart from this side because it is easier to compute gradients from left side. And there is a mathematical computation to it. Okay. Backpropagation is really mean loss will come only after all of up, absolutely, unless you actually compute all of the loss samples, all of the examples in your x underscore train. It will be, no, not integration, everything is differentiation. After you compute all your examples, then only you can do the divide by n part, right? Okay. Do you understand now what is the core of understanding of backpropagation? So this is what exactly backpropagation uses. It gets little bit more complicated, but I think we should, understand this and move on with our. I think we should move on with our understanding, and then we'll come back to this at a later date. There are a lot of opportunities of opening up backpropagation again and again and again. So don't worry about that. Let's do one thing. Let us go to the PDF, right? Sorry, the PPT, and see if there is too much deviation on that, right? So this is what the feed forward network is, right? Each of them weights has some values, right? That's what we did. We've calculated it. In this case, what they have done is that instead of ReLU, they are considering the logistic function. which is nothing but the sigmoid. Sigmoid looks like this. Okay, I did not want it to add the mathematical equation of the ReLU, but I just showed you that how to compute that. Now if you actually unravel the actual equations, so the dy dx, or the d of ReLU to the d of w, will be a little bit like this. Okay, so you compute what will be your output for that particular layer. This is actually a one layer network. Okay, this is your input. Okay, this is your hidden layer, and this is your output. Right, is that okay? And then you compute your forward pass, and then you calculate your final total for each of the outputs. Right, and that is how many outputs you have. You have two outputs, basically two samples, and that is what you do. That is why you do 1 by 2, because there are two outputs, basically two samples that you have. Right, you've come to a 0.9 is something that I've taken from here as it is. Okay, that's why it stuck to my head. So this is my forward pass. I've calculated my loss. What happens in back propagation? The same thing that we saw, the similar sort of things. Given my error total, I need to compute my gradient of W5. And to compute my gradient of W5, I need to compute gradient for each layer and each layer's gradient. And this is where I will use chain rule to finally compute gradient of each of those layers. Okay. So now it has W5. So there are 3 steps to this, right? So if you actually, we'll just go through it one, and then we can go to the, we'll see for the others. So it's like there are how many weights we have. If you actually go back to the network here, there are W1, W2, W3. So there are 8 weights, right? So he's talking about only W5. So this is only talking about W5. The way you will compute W5 is, right? So this is the 3 partial derivatives you calculate, right? And this is how you first calculate the first partial derivative, and this is the value that you get. This is the second partial derivative in the same equation. I am still trying to find out d of loss for one specific weight, a single weight, remember that. Okay, and then the third partial derivative, and then I multiply them. If I multiply them, I get my 3 partial derivative, and this is what I get. Okay, remember one thing, backward propagation. So let's do one thing. Let's go here. So backward propagation gives me that what? Okay, this is a little bit interesting to understand. It tells me the change. I've got the change, but it does not apply the change. Okay, it will never apply the change. It will only give you new gradients. It will tell you, here, look, I have back propagated through each of your layers, and I have found out that if you change each of your weights by this much quantum, you will have a loss reduction. That's what it will tell, and it will have that's what it will tell, that please use this. It's a suggestion that it will give you. Who will apply the change? Someone else will apply the change. Who will apply the change? Can anyone tell who will apply the change? There is a special algorithm which actually applies the change. The actual change in the W, that's where the learning rate will come. That will be applied somewhere else. So let's look at where does it apply. Okay. So who does this weight updation? So weight updation. So you have this new weight, right? I have to update the weight, right? I have got a new gradient, right? So this is my gradient that I've got, d of loss divided by d of w, right? So this is what I just explained, right? Backward propagation. This is exactly what I explained right now. Backward propagation, right? I just explained backward propagation, Suchita. Right? So I'll just explain one more time. Maybe what I'll do is let me explain one more time. At the end of it, let's find some time, and I'll explain it one more time. Okay. Okay. Let's do that once. So essentially, what I'll do is I'll compute the gradient of this particular weight, right? Given my loss. So this is what I computed. How did I compute it? I use my chain rule, right? As many number of layers, I will calculate my partial derivatives, and I will calculate it, and then this is the rule via which I will apply my new weight to my W. Basically I will have a new W5, and this is, you see this eta value. Someone was saying that what is learning rate? This is my eta value, and this eta value will be used at this time. Who can anyone tell who does this particular weight updation? Who will do this weight updation? Who exactly will do weight updation in the scheme of all our, we've gone through multiple algorithms, right? We have a learning algorithms, we have a loss functions, and then we also have one more function, which is an optimizer, right? Do you remember what is the objective of optimizer? What does the optimizer does? And we will actually have a detailed session on optimizer, okay? On chapter 5, if I'm not wrong. So what does optimizer do? Optimizer, not global minima. What does optimizer do? Optimizer helps in reducing the loss. How does it reduces the loss? What does optimizer does? What is the definition of an optimizer? We have gone through it. What was the definition of an optimizer? An optimizer, okay, let's go through it one more time. It's there actually, we covered it yesterday. So this is what it is, right? It's descending, right? Next step is lower, 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 right? We have converged, right? We have found out a lower point, right? And when we have got a lower point, right, we have to move, right? So optimizer, this is where we have to, we are moving down the gradient, but we have to apply the new weights. Optimizer is the one which actually applies the new weight based on the gradient that is computed by the backward propagation algorithm, right? Okay. So again, one more time, let's go back this. Suchita asked that can we one more time brief explanation of backward propagation. So now that we've understood forward pass is all about, loss is nothing but a function of W, right? So if we have to change loss towards 0, if we have to push loss towards 0, we need to change W, right? And the equation to change W, so we need to basically compute a partial derivative of this equation. So we need to find out equation of, we have to solve this equation, dl by dw. How do we solve in mathematics? Using a function called as chain rule, using a theorem called as chain rule, okay? And the chain rule will look like this, okay? This is nothing but, this is basically for, so dl by dw will be expanded based on how many number of functions your learning function has produced. In our case, we have decided that we have 4 learning functions, right? Or 5 learning functions, right? We have 1, 2, 3, 4. So in this case, we have to solve 4 partial derivatives to reach to this number for every weight. This computation has to happen for each and every weight, right? And that is what backward propagation will do for each and every weight. It will apply this logic of chain rule and compute for that delta, that gradient for each of the weights and keep it ready for the optimizer to apply it. Okay, is that understood now? Suchita, is it clear? Is it better now? Yeah, it's better now, right? Don't worry, we'll have to come back to this again and again and again. If your neural network does not work, the only way you can solve is via this, this part where you actually have to, why it is not solving, right? Why it is not, diverging to a loss, right? You need to go back to this again and again. And we will come back. We'll come back to this again and again and different layers. Right now, just understand this concept that forward pass and backward pass. Forward pass is something that we understood. Backward pass uses chain rule. Okay, for every such layer, I have to find differential partial derivative against the loss for that weight for every layer. In other way, you can ask that how much this particular layer is contributing to my loss. Other way, you can say that how much each of my neuron or each of my weights is contributing to my loss. I need to compute that. So think about it. If we are talking about the 300 million parameters, the model, or that Google model, right, in 2017. Think of the computational need that backward propagation has to do. It has to compute gradient for 300 million parameters for each and every sample, right? Isn't it? It's a massive mathematical operation, isn't it? So backward propagation also does some sort of computational improvement to ensure that it can handle such large matrix multiplication and it's a differential equation. It's a large, really large differential equation, right? So that is what, as of now you should know, and then we'll move on. We'll go to the layers after layers of layers of this. Now you understood, right, why it is so complicated. With just 3 of the layers itself, our function looks like this. Imagine if it is 1,000 layers, what will happen? What does TensorFlow or any of these frameworks does? They use something called as a computational graphs. Okay. If you have heard of it, good. But if you have not, it's fine. It's a new word. Okay. Computational graph is a branch of mathematics. What it does is that it creates graphs like this. Okay. Okay. And these are basically functional graphs. Okay. It's actually mathematics. What it does is all of these are functions, and these are dy dx gradients. Okay. So TensorFlow provides you a graph internally, and this can be easily computed. That's why it is TensorFlow is such a powerful thing. You cannot do all these things with if constructs and else constructs. You need something of a computational graph to compute this at this scale. Okay. And again, so if you do this for 10,000 times, right, you will reach somewhere else. Right? Okay. Awesome. Shall we quickly go to activation function? I wanted to actually, it's fine, we have time. That's fine. Absolutely. So this is basically one pass, isn't it? What we did, we just did one pass. For one sample, we computed the loss of one pass, right? We need to again go back and do it for us. So computationally what happens, this is a large metric multiplication. Okay, you can give this thing, this is instead of one, okay, instead of one, this is basically one sample I'm giving you, right? So this is nothing but one sample one, right? If you give the input like something like this, I'm just saying, okay, I'm just saying, suppose, okay, so this means that I'm giving it 2 samples at a time, right? But I'll be able to compute it, right? So each row represents 2 samples. Loss will not be then scalar, it will be a matrix again. What it means is that it will be something like this, okay, 0.5, which means my first sample, for the first sample my loss was 0.29, my second sample is 0.5, right? So and then you can actually aggregate at the same. So this is all of this, hence matrix or tensor is a right data structure. Tensor is nothing but the right data structure to pass around, because all this computation you can imagine, right? It will not be a for loop kind of thing. It's impossible to do it, right? And n will be also pretty large, right? If you have 1,000,000 samples and you have 1,000 layers, you have 1,000,000 weights, it's virtually impossible to compute such things, and it will take ever, how much ever compute power you have. So hence all these mathematical operations happens at a tensor level, right? At a matrix level. So basically data of data of data. And the maths of this, because this maths of this is not, mathematics doesn't have a problem with to deal with these things, right? It can take any of the construct. That's the reason matrix multiplication is so important. Okay, clear? Any other questions on backprop? Now I can guarantee you one thing: we will do at least 2 more rounds of backprop. Okay, because when we actually go to optimization, we'll have to again do backprop. So what happens is that many a times what happens, you need to create your own custom layer. You need to provide your custom forward and backward propagation, and you have to ensure that if you want to train something, you want the model to run, ensure that it goes via the backward propagation system, so that the weights and biases can be learned by the model, not memorized or not hard coded. Okay. I'll definitely find out. I think the LMS has, she has told, right? I'll definitely find out a way to share this. Let's just understand this and go move ahead. Okay. So let's come back to activation functions. We've spoken about a lot on activation functions. We have understood that there are many, but what are those? What does it give me? So activation functions are nothing but, they introduce non-linearity in the network. Without the activation function, everything will become linear, right? Basically, it will basically fall down to it will be a bigger linear network, and that's about it. So activation functions are the non-linear functions, and that is what they give you the hidden representation. They basically bring out the hidden representations. Okay, I will share the notes. Definitely, I'll share the notes. Okay. So what are the activation functions that we have gone through till now? So let's look at sigmoid. This is the function of sigmoid, right? What is the function? 1 by divided by 1 plus e to the power minus x, right? What is its properties? Its properties is that it's a value that it will be squashed and between 0 and 1, right? Sigmoid, so it will be between 0 and 1, right? So it's a real value number squashed into a range of 0 and 1. Sigmoid neurons, if you have a neurons, and if you use sigmoids in the hidden layers, there is possibility that your learning might stop, and we will look at this. There is a problem in neural network called as vanishing or exploding gradients, because if you're one thing is very clear, right? Your backprop, let's go backprop again. If your gradient, this gradient computation, right? Any of the gradient computation is 0, what happens to the whole gradient? Anyone? It will become 0, right? Anything multiplied by 0 is anyway 0. So we have to ensure that everything will become 0, right? Everything will become 0, right? So that is what I think we should be worrying about. So neural network face this problem a lot of vanishing or exploding gradient, and that you have to ensure that. Okay, we will share the today's note, don't worry, this note we will share, but we should have everything on the practice lab, right? Everything whatever we have shown is everything on the practice lab itself. If you have gone there, you should be able to access them, right? Okay. So that's what this is what sigmoid is, and we will discuss. There's a better version of sigmoid, which is tan h. Tan h formula is something like this, and which is 2 divided by 1 plus e to the power minus 6, and then you do a minus 1. It is generally between minus 1 to plus 1. It's little. If you think about it, that if you are doing differentiation on this function, sorry, right? We have to figure it out how to do it, right? So that's what it is. So tan h does not like sigmoid. Tan h is so they also do saturation, but this is actually a real value between minus 1 and plus 1. Okay, and this is, so you see that it's actually zero center. Sigmoid is actually not zero center. Zero center means the center of this curve, right, is actually 0. And the rest is a minus 1 plus 1. Yeah.
Hi, Sandeepan. Yeah, sorry to this, sir, but can you show the learners once again how to access the practice labs and the questions and the notes which are currently over there if they have any doubts?
I will do that, right?
Thank you so much.
Okay. So what's ReLU? ReLU is something that we've discussed, right, for on activation function, right? ReLU is nothing but f of x 0 or x. So basically, if x is less than 0, then it's going to be x, and if x is anything greater than, so the value of ReLU basically will cut something like this. Anything above 0, it will be that value, or anything below 0, it will be 0, right? So any negative value, if you pass it via ReLU, it will stop it at 0, right? There are a lot of different formulation of ReLU, right? We have leaky ReLU, we have eReLU, we have parametric ReLU, and so on and so forth. But they all have their plus minuses. This is like for ReLU, right? This part is totally 0. So this also has some sort of vanishing gradient, but very, very large networks, what happens is that if you have a very, very large network, this problem reoccurs, right? This vanishing gradient problem reoccurs because what happens, one of the partial derivatives will become 0, which will make the gradient of the new weight, right, with 0 ultimately. So that is what we have to worry about. Praveen Pandey is saying, but how and when? Praveen, can you explain what is how and when? Okay, fine. So we are almost there. So what we'll do is like we will now go to practice labs, right? And focus our time there. Maybe before that, let's go to practice labs. Okay. So this is exactly the right time to practice lab. Okay. You're I'm asking about notes. So notes are so this note is something that I made, Praveen. This note was made by me today, like just before the class, for me to explain to you, right? So this I can only send it after the class, isn't it? Right? So everything else is in practice labs. Let's do one thing. Let's go to the practice lab now. Everything else is in practice lab. Okay, right? I'm assuming that. So now if you actually go to self learning, right? If you go to self learning, right? So you can see this code, right? You can I can my screen is already shared. So this the node that I just showed you is actually something that I created before the meeting, before the today's session, because there was a question that can we go through the crux of forward and backward propagation, and that is what I explained, which I will share. Okay. Okay, I would encourage everyone to move to practice lab, and then let's open our, open your, Jupyter Lab notebook. And just to clarify, if you can see my screen, this is the place you can see all your code, right? You can see you can download the code from here, right? This is the practice code. This is from our previous session, isn't it? And you can do this from here, isn't it? And this is what we'll do. Right? So if you haven't downloaded, can you download all of them? And let me in the meantime open my practice lab as well. Please open your Jupyter Lab notebooks in the Simply Learn practice lab and give me a shout out once that is done. Okay. Let me know, guys, if you are. Okay, why do we use ReLU? If you use sigmoid, right, it's not differentiable. Softmax is generally used at the last. One second. Softmax is generally always used at the last layer, okay, to generate probability. ReLU, what happens is that it helps you to handle the vanishing gradient problem. We will look into that. We will definitely look into that when we go to the optimization, right? We will look into that in closer detail. Why ReLU works better than everything else, because it helps us to the problem of vanishing gradient. Everything else goes makes increases the possibility of vanishing gradient, because what happens is that when you're going back and computing the gradients, one of the term can easily become zero. You have to understand one thing. Now the anything above 10 layers, 15 layers, right? Tan H sigmoid will not work. They generally tend not to work because of the vanishing gradient problem. ReLU has been working pretty great. In fact, nowadays the networks are so large, ReLU also is sometimes not working. So what has been improved on is there is something called as leaky ReLU. The elbow part, the left part of ReLU, in fact this part of ReLU, right? This is right. This is not exactly zero. So it will never be zero. It will little bit tilted so that it never becomes zero. There is also a version of ReLU called as pReLU. Now you can ask the model to train that how much should be tilted. Okay, so there are multiple versions of ReLU itself, right? Okay, so let's go to lesson 3. Okay, have we all opened this? Let's open. We have looked at lesson. We have looked at. Let me. Yeah, so cancel this. So let me just cancel this. Okay. discard, and this is what we will look at. Okay, this is what an assisted one, if you remember, we have looked at it, the first day itself, where so this is also, let me just close it, and I will actually open the assisted 2 is something that we have gone through that. You don't see these 2 files at all? So how can we help? How do we? Have you actually gone here? No files. Okay, this is very strange. Have you gone to self-learning and downloaded these files? This thing, can you see my screen? Can you just go to 3.7 and then download it? Yeah. Okay. Who has? Oh, you have raised tickets. Okay. LSM, can you help us here? I think what has been said here is that they don't have access to 3.7 and 3.4. That is correct. Yeah, go there, you download this link. This is a Jupyter notebook. Yeah, so you download it. So what I did is like I downloaded all the codes and uploaded it like this. Yeah, and you have to upload it in the Jupyter Lab. If I'm not wrong, we have done this on the first day, right? We have showed it how to do it, right? Okay. Not there for you also. So there seems to be a problem. There seems to be a problem. Who can? So let me just talk to LSM. Yeah.
Hi, Sandeepan.
Yeah. Hey. There seems to be a
Yeah.
problem that people are not able to access they are not able to see this particular 3.7 or 3.4 where you have the Python notebook. Okay. Some have, some don't have. Actually, not everybody has.
Okay.
In fact,
Okay.
what is being said here is that some of them have actually raised tickets. Okay.
Uh-huh.
And you can see that people are saying that only 3.5 and 3.6 is visible. Some doesn't have
Okay.
3.7 and of various degrees. Is it possible to get this thing sorted out somehow?
Yeah, sure, Sandeepan. I will talk to the technical team and I will get back to you soon.
So that soon means that we'll know something by in this by today itself, by now itself.
Yeah,
Or?
I'm trying to work on it as soon as possible between the sessions, and I'm trying to get a solution within half an hour if possible. And if there is any update, I'll tell you soon.
Okay, guys, you have heard, right? So some doesn't have some various degrees of problems that is there. Okay, I think
Okay.
she will try to help us. Some doesn't even access to this lesson 3. Some doesn't have access to this particular section itself. And
Okay.
I would request you to, if that is possible, then can we also have a shared Google Drive or in some way so that I can share these things. Okay, is it possible that
Okay, sure,
can I email them right away to you? And is it possible to?
Yes, if you email me the files, I will be sending it to the learners now, and I
Okay.
will definitely update
Let me
about
do
the
one thing.
details in
Let me
the lab.
Yeah. So let me guys, let me do one thing. Let me send today's and tomorrow's file today right now itself so that you have that ready and so that you can upload it to the practice labs. Okay. Irrespective of whether they're available right now or not. Let me just send it to. Can you send me an
Yeah,
email?
I'll share my mail ID with you, Sandeepan. And everyone, so Google Drive is currently under maintenance and we are not able to share files in Google Drive, and we will be emailing you all the necessary files soon. And we are also working on the Jupyter Lab issue. I have raised it from my end and we will soon get back to you with the result.
Right.
Thank you so much, Sandeepan. Yeah, I'll be sharing you my mail ID.
Yeah, please share it so that I can.
Sure.
So what we'll do, guys? Then let's do one thing. Let's solve this problem of not getting access to the files today, and let's just complete. We have about 3 more minutes, 4 more minutes, right? Let's just complete our PPT of lesson 3 and we'll take a short break. Let's take a short break today. Is it okay that if we take maybe not a 15-minute, maybe 10-minute break, and by the time we hope that we come back and these problems are solved somehow and you have access, and then we'll spend quantum of our time on at least 30-40 minutes on, no, maybe 20-30 minutes on Jupyter Lab, and then we can start our session 4. Okay, so let's does that work for us? Okay. 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 Just 1 second, guys. Let me actually email this. Okay. Let me just email once. Okay. Right. So this is something that, so this was the code that we will actually go through it. No point in going through here. We will actually go to the code. So let's talk about, so we have basically 2 topics that we are left with. One is regularization, and so what is regularization? Does anyone know what is regularization? What do you mean by regularization? Anyone? Where do we need regularization? Penalizing what? Why do we need to regularize? You have to penalize the loss functions. The thing is that generally every model, and more so machine learning models, right? And deep learning model also, they have a tendency to memorize the training data. Not reducing error, everything else is fine. Yeah. So they have a tendency to memorize too well. If you have suppose 1,000 data sets and you have built a very deep network, right? Which means that you know the pattern so well of the data that it will perform extremely well. You will get an accuracy of 1. Okay. And if it performs extremely well, which means the model is generally not generalized, right? For whatever reason. So for that, you need to ensure that the model doesn't memorize or learns too well the training data, and for that we would use regularization parameter. We have the same concept in our traditional machine learning as well, and what generally happens is that the regularization parameter is, in a way, impacts your final loss value. So we have this loss value, right? This loss value we have, right? So generally what happens is that the loss is like this, right? So what happens is that a regularization parameter is added here. Okay, you add a regularization parameter, sorry, actually remove this. So basically with this particular loss function, you do plus some regularization function. Okay, there's some, you have to do, I mean, there's some regularization function. Okay, so just put an n in front of it, right? So this is an extra parameter, which means that if your loss is very, 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 very low, like almost zero, zero means what, you are learning too well, right? Then the regularization parameter will be like this, so that in the you will not let you become too well, right? And now that you've understood that everything is a function, you now understand that this is also a function, right? Hence this component gets added to your this large component. So your dl by dw will also be making sure it's actually differentiating, or there's some sort of partial derivative of your regularization function as well, right? Because since you are doing dl by dw, but the fundamental reason of doing regularization is nothing but ensuring that it doesn't overfit, right? So that's one of the reasons that you have to regularize something, right? What are the way? So this is a very, very typical graph. Nothing changes. This is the same thing that we have in in typically machine learning also, right? If your epochs are this and your error rate is this, if your green line is nothing but your training data, right? So your green line is nothing but your training data, whatever, yeah, right? And if your green line is going down and down and down, right? All it means is that it is just trying to learn a lot. And your blue line, which is your validation data, at this point it starts to go up. Typically, till the point that they are all parallel to each other, it is fine. But when at this point, at this red point, you should when you see that the validation data is actually getting higher, but your training accuracy is actually been maintained and in fact going down, you know that you have actually found out a point where overfitting has started, right? And this overfitting can be controlled in a neural network by an algorithm called as early stopping. What happens is that it detects that, okay, this is the point of inflection, something is happening here, we have to stop we have to stop something, please do not train, and at that point the training will stop, right? And it will do something else, right? So that's essentially what it is. The this sort of graph generally will indicate that your model will not generalize well, okay, because it has memorized your training data all too well, okay. How do we deal? How do we deal with regularization? Can anyone tell one of the regularization algorithm in traditional machine learning? Anyone? Yeah. One more. Since we spoke about lasso. No, what is the ridge and lasso regularization, not regression. Ridge on lasso regression, right? Sorry, regularization. Do we remember what the equation of ridge and lasso? Both are similar, but there's a little bit difference. Do you remember? One does a square, one does not do a square, right? If you remember, if you do a square, it just penalizes really, really high, and another one just use the magnitude of it, right? It doesn't use the sign of it. So similarly with what we have, yes, lasso does not. Correct. Perfect. So same thing here as well in TensorFlow or in neural network also. You have L1, you have L2, both regularization. In fact, you have L1, you have L1, L2 regularization as well, right? So this is what I was talking about. See, your cost function or your loss function, whatever you have, you add the regularization parameter to the loss functions. Remember that, okay? That is very important for you to understand, okay? There is one more way to handle comes down by adding to the cost function to the large or to the for large weight. Yeah, so essentially what, again, where do you add regularization in this whole architecture? We add regularization anywhere else? We did not. What happens is that regularization gets added as part of the loss function plus regularization here itself. So if you add it here, this is where you add it. So you ensure that this thing will ensure that the other component will be penalized, right? This ensures that, come to think of it, if you actually think, right, this part is truly on 100% only from data set that you drew. This is only and only from Xtrain, right? If you do not have this, right, if you do not have this, see, the thing is that if you don't have this parameter at all, think of this particular term in loss is nothing but everything coming from Xtrain, right? So then that means that you are by default going to be overfit if you do not have this term at all, right? Because there is nothing else here. This is all about Xtrain, this part. So you must be adding a regularization parameter to ensure that you don't overfit, right? So that's the intuition behind it, right? However, in neural network, there are multiple ways of regularization. L1, L2 is definitely there. You can also build your own regularization. There is a special regularization layer itself. Okay, is it time for the break? We'll just take a break. Okay, let's just finish this thing and we'll take a break. Okay, 2 minutes, and then we can come back again. Let's talk about dropout. So dropout is a special regularization layer. What it does is that, very simple idea, that it randomly switches off certain neurons. Okay, if you add this layer, it will randomly not pass the neurons. Basically, in this case, in this particular layer, you just added a dropout layer. What it will do is like, it will only pass this neuron, but it will not pass these two neurons. Okay, that's what it is. Okay, guys, let's do one thing. Let's take a break, and then when we'll come back, in the meanwhile, I will email all the things so that we can start our work there. Okay, thanks a lot.
Hi, sorry, Sandeepan.
Yeah.
So before going on the break, so all of you just please ensure that the Jupyter Lab is updated from your end, because the issue can also appear if the lab is not updated also. So please click on the three dots near your course card and try to update it if it is not updated, while we are also trying to find out the problem from our end, and we will connect with Sandeepan during the break.
Yes, please. Okay. Yeah. Thank you, guys. Okay.
Thank you, everyone.
Okay, folks, shall we regroup? Are you able to open your, Jupyter Lab environment in Simplilearn? And you can, and in fact, I have PDF link I have shared that day itself, if you remember. Okay, it's a very simple. So Turing test, that's a good one. Alan Turing You know what? We have the largest neural network of all time in your hand. Largest Alan Turing PDF, right? So this is, I think this is the one. AM Turing. Yeah, you can use this. Actually, not this one. Yeah, you can try, you can read this one. Yeah, this is from yeah. So this is actually, there is also a ResearchGate. We can actually go to archives. Archives will also have PDF available. Download file as PDF. Yeah. So I'm just putting this. Yeah. So this is one of those links from 1950 paper of imitation game. Yeah. Okay. Okay, let's start. Let's start on the practice labs. I hope you have all the things that is needed. And I have actually sent all the information, including the notes file. Okay, the cleaned notes file. Did not wanted to send you guys so many scribbles so that at least you're not confused with this. Right, make your own scribble is what I say. But I hope they'll reach you in time. So let's start on the practice ground. And before that, let's see what do we have left. Okay. So what we are trying to say here is that let's complete our overfitting problem and discuss a little bit of overfitting. So we understood that overfitting is something that is accompanied with loss, right? And it penalizes if you're trying to, so the training cycle must be, sorry, the loss must be penalized if you're trying to learn too well. Essentially, if it becomes too zero towards really low, ensure that it is not that low, right? Apart from your L1, L2 regularization, you also have a special sort of technique in neural network via you don't have the IP1B5. I think it must be on your way. Okay, so I've just forwarded that, okay, to the mail ID that I've given. So I think it will come via email or in some form it will come, right? So they are fixing it, right? That's what they say. So let's understand what is dropout. So dropout exactly does this, right? Oh, this is actually not good. Yeah, I think they're fixing out all the issues, right? Yeah. So so what does dropout does? Dropout adds a new layer, and it basically randomly switch on switch off neurons. When you say it switches off, okay, which means that it will not allow you to allow the anything to pass through it. So no summation, no weights, nothing. So essentially this will be a zero. So it doesn't mean that your output will be, suppose, let's go back to our our neural network, and if you see here, suppose we add a dropout just after this ReLU here, right? Or maybe after the H2 layer. What will happen is that after this layer we have to add it somewhere over here, right? We can add it here, right? If we add it here, or maybe we'll add it here, so one of these neurons will become zero, right? That's all it is, right? Or randomly any of the three neurons will become zero, right? So the shape doesn't change, however the value of neuron becomes zero, which also means that while doing backward propagation there is nothing to check there, right? You still have to implement your back prop and forward pass, but randomly choose that some neuron and switch it off. That's all it is. And you can choose an hyperparameter. The dropout as a layer has an hyperparameter that you can choose, right? How many such neurons that you want to switch off. So it's basically considered via a layer. It makes sense to put things via layers, right? Then what happens is that the good thing about this layer is that you can build a composite function like this, right? Function of function of function of function of function, isn't it? And if you can do that, then remember what happens. Nice things happens, right? You can easily compute the loss, and then you can back propagate as well as, so forward propagate, as well as the most important thing is backward propagate. Hence neural networks approach is to take this function of function of function of function of values, right? And everything is nothing but a layer. If you want to add your own custom layer, put your own custom layer and do with it. And we will see this theme going on, right? For convolution neural network, we will see that the layer it's a layer with some special properties of that layer, right? So that is what exactly what dropout does. If you actually see, right, and how does it ensures regularization? Okay, what does it ensure? Can you guys tell me how does dropout ensures regularization? How does it ensure that there is some sort of that the model doesn't learn everything? See, the thing is that on every pass, when you suppose you are doing one forward pass, in the first forward pass, what happens is that your maybe the second neuron is switched off. On the third forward pass, your third neuron might be switched off. So in any of the pass, the layers will not get the same values. So in a way, the layer is not the model, or at least in that particular pass, is not seeing the same things. Hence, it is ensuring that you are generalizing more. It is almost like this concept of, bootstrapping in random forest. If you remember what was that, right? For every small tree, you will bootstrap the data in such a way that every new small D tree model will look at something else, right? Like different parts of it. Dropout works out like that. It will switch off some neurons in the hope that you see only some parts of the data, not the same parts of the data all the time. So that's how from an intuition standpoint, I think that is what it is. And there was some experiment done on this architecture on the MNIST data sets that what we are using, right? So if you see MNIST data set is what 28 into 28, right? What is MNIST data set? 28 into 28, which is 784 data set. And suppose you have a two-layer network, three-layer network, right? Sorry, four-layer networks. Each of these networks has 2048 neuron, 2048 neurons, 2048 neuron, and last layer will be how much? So if you have to solve MNIST, what will be the last layer? How many neurons you should have in the last layer? 9 or 10? Yeah, 0 to 9 is 10. Yeah, so 0 to 9 is 10. So 0 to 9, 0 is also a class, right? Remember that. Okay, so there are 10 classes, hence 10. So you can see this, right? So if someone asks you that what is this means, that this clearly means that this is a four-layer network. We generally don't consider input layer as a layer, because input is data, right? It's not exactly, because to become a layer you have to pass through the summation and activation function, right? Input is just input. So 784 is the input, and then it's a four-layer network. Last one will be basically softmax. So if you actually added a dropout rate of, you can say the dropout rate of whatever it is, and you will see that this graph is produced, where the model is the blue is the training error, okay, and the green is a test error against a probability of retaining a unit, right? If you continue to return a unit, right, so it's somewhere over here, right? So, and basically you will see that your classification error on the test improves, right? You should actually see the classification error on the test decreases, right, if you have some sort of dropout. And in fact, it's been observed that the best dropout rate is around 0.5. The training error is low, somewhere over here, right? Low enough. But if you drop out too much, you will start missing information. That is also not that great. But if you drop out just about right, and that's something that we have to fine tune as part of hyperparameter tuning, you might get a really good value around it. Okay. Okay. Can you see now? I just reshared it one more time. Yeah. Okay. So basically, this is what I was saying. If you drop out at the right time, the right frequency, at the right value, you will get a good error rate. If you don't drop out at the right place, you might actually lose. If you have too much dropout rate, you are stopping lots of neurons from processing. But if you have too low dropout rates, you're again, it's basically almost equal to what the training data is giving, right? So achieving the dropout rate, right dropout rate, is can be treated as a part of your hyperparameter tuning, right? Okay, let's let's, without wasting our time, because let's go here and then this have to refresh. Let me refresh it again. Okay, please guys refresh it. Have you guys got the files? If you have got the files, if you haven't got the files, please shout out. And any update that when can we get the files to the learners? Okay, they haven't. Okay, so shall we then? What shall we do? We should start, and maybe you can. So we should start, and then I'm just trying to think. Okay, let's start. You are not supposed to. What do you mean by are you supposed to upload the files? Yes, of course. You have to upload the file to Jupyter Lab in the practice. This is a VM, right? You have to upload the file once you download from the self-learning tab. Okay. Shall we do this? Assisted 2. Assisted 2 is also a, we can do it together, right? What are the files to upload? Okay, that's interesting. Shall we just, so if you actually go to 3.7, can you see 3.7? Can you download this? Can you click on this button? Yeah. So now can you come to practice lab? And you can upload. Click on this plus, this upload button. When you click on this upload button, choose that file to upload. And that will upload your IPYNB file, which is the Jupyter notebook. That's all you have to do. Okay? What say, folks? Shall we start? Yeah. So this is something similar to that we saw. We did yesterday, remember, MNIST, and I have shared these files. You will receive it whenever you receive it. Assisted 1, yesterday only we did it, right? How to get assisted 1? Okay. Let's go to 3.4. Can you go to 3.4? Yeah, so just download it. And at this point, I think it is extremely important. Now I realize what's happening. So just download this, do the same process. All of you, whoever hasn't understood it, please go to the lesson 1 and please look at 1.2 very, very well. There's a video on how to access Practice Lab. That is point number 1. Point number 2 is, on the course that we are in, please come to your self-learning. This is to the people who can actually see the lessons. There might be some people who are not able to see it, and I think I know LMS is trying to solve them, so don't worry about those. If you can see this, right, there will be something written called as assisted, unassisted, right? This means these are projects, these are practice projects that we will do. Okay, some we will do, some you have to do, right? As of today, we have completed, introduction to deep learning. And we have yesterday, if you remember, we've completed 3.1. We have also completed one sample MNIST on its own. Today, what we will do, we will complete assisted 2, right? Assisted 2 will be fairly easy cakewalk for you guys, because you have actually done forward pass and backward pass in a much complicated way. You've understood things now. Okay. So now going forward, what you have to do is, like, you also have to complete your practice project. After the before tomorrow's session, you start, right? You can see these things, right? 3. And all of this, and then there is a 3.14. You can see this is a lesson end project. We have completed the lesson as of today. You have to, because we have completed all of it, right? Except probably regularization and optimization. We'll look into this, right? So optimization is also there in lesson 5 in detail. Okay, and that's going to be very, very interesting thing. So here 3.14 is a lesson end project. If you go there, I'm just going there for everyone's benefit. You see there's 2 links to it. The link number 1 is the file. Okay, the proposed solution. Ideally, I would request you to, code it on your own. And if you want to see the solution, you can see it. And you would need that, the MNIST data. You can download this from this Dropbox link. Okay, the description of the problem is given. What do we have to do is given, and you can do it in your practice lab. Okay. Okay, fair enough. Okay, yes sir, please Shobha, please tell me. Please go ahead, Shobha. So there is only one file. You see that if you download it, right, they will be in a zip format, right? If you download 3.4, that will be in a zip format, right? Can you unzip them and then upload it? It will be a file by name assisted space one dot zip. Sorry, dot ipynb. I assume. Okay, I'm just, I think that's how it will be. And the 3.7 will be another zip file. If you unzip it, it will be assisted 2 dot ipynb. Okay, this is how it's going to be. Okay, no worries. Yeah, no worries. Yes, please go ahead. I think this is important. Let's spend some time to understand that if you have any problem in accessing things, upload done. Okay, upload to where done? Upload to Jupyter Lab is done. Okay, fair enough. And now if you actually double click it, you will see you can see my screen. You will actually see something similar, right? You will see something similar. This opens your Google Jupyter Lab. This is nothing but a Python interpreter, IPython interpreter lab, via which you can code Python programming. Okay, and if you open it, okay, ideally I would want you to actually code, but that's fine. For now, it's fine. You can actually execute things on its own. One of the prerequisites of this course is Python. I am assuming that going forward, we will, you will be knowing Python and a bit of machine learning. Okay, right? Let's let's proceed on this, guys. Okay, I think we are running a little bit late, but let's proceed. So what are we going to do? We're going to do something pretty simple. Okay, we will build let's go to the problem statement, right? It was nicely written. Where was this problem statement? I think this is the problem. We'll build a neural network. Okay, write a very simple neural network considering the activation function as tanh. In this case, I think we will use tanh. Okay, but it's in the same line that we will actually build a neural network without anything of TensorFlow whatsoever, with whatever knowledge that we have, right? And with only NumPy and whatever we need from everything else. Okay, this is exponential array random and dot operation, right? So what we'll do is like this topic is hi Priyanka. Priyanka is saying that hi Sandeepan, see I am getting this error. This topic is covered in our live class. Live. Okay. Can anyone help Priyanka here? Priyanka, no. Priyanka, can you actually raise a ticket? Have you raised a ticket on this? Can you raise it? The easiest way to raise it is, yeah. Can you please raise it here? Please raise a ticket. Okay, the best way to raise it, go to your dashboard of LMS, okay, and raise it right away. Okay, so that at least this should not be a problem. Okay, so let's just run it. Okay, it's very simple. So basically that's it, done. So I'm just trying to find out. Let's try to see what has happened here. We are building a class. What is the first thing that a class would need? We need some sort of initializer. We need to randomly initiate something, right? And what are the things that we have to? What do we randomly initiate? What do we randomly initiate, guys? We have to randomly initiate for the first time, right? Whenever the class is any this, we randomly initiate weights as well as biases. Here in this case we are not talking about biases, but weights as well as biases. In this case the is very nicely named. Synaptic weights. Synaptic weights are nothing but linked to a biological neurons, right? We in artificial neural network world we only talk about weights and biases, but essentially in brain it's called as synaptic weights, right? And there is some sort of random function that is used 2 into rand of some random function between 3 and 1, and then you do a -1 operation. Okay, we model a single neuron with 3 inputs and 1 output connection. Okay, we assign a random weight to 3 by 1 matrix. So essentially this will give me a 3 by 1 matrix which is ranging from -1 to 1. But what I'm trying to say here is that you are starting some sort of initialization. You have to initialize the weight, right? Now what is this? Tan h will then be what? What is the tan h function? Do we remember what was tan h function we just discussed? Tan h is nothing but an activation function, right? A neural network on its own must have an activation function, and it has a value of -1 to 1. It looks very simple because if you use NumPy, NumPy has a tan h implementation. You can just as it is use it, right? As simple as that. And but then we saw 2 implementation yesterday. Remember, we saw that each of those we went via layer wise implementation, and now we are seeing function wise implementation. If you are using tan h, we need to give a derivative as well, and derivative of tan h can be considered like this, right? So that's what we did. So now that's it. That's the only thing. So where did we do aggregation? We have not done the aggregation yet, right? So we have only given the. So in this case, all we did is the all we did is the. So Priyanka, I think you are talking to LMS, I guess, or I'm assuming that you are talking to the support here. Okay, I'll continue with the IPYM with the practice itself. Okay, thank you very much. Okay, so that's fairly simple. Now let's go to train. What does train look like? Train is exactly like this. Okay, what do we know? How do we train? We should be able to add a layer. So this was our holder, the object, right? And we have to add a layer, and we have to add a optimizer. So essentially train is nothing but do a forward pass, compute loss, do backward pass, keep your weights ready, and then use an optimizer to update the weights, right? That is what it will gonna be. So, and of course what we will do is like we will iterate against many iterations, right? In this case we'll parameterize this, right? So training wise we'll take some inputs, the training will have an output, typically the result of the training, right? And number of iterations. 3 is fine for us now, right? For every such iteration we'll have to think. This is a nicely thing. So self.think. What is self.think? Where is think implementation? Think is this. Think is nothing but, what is think? Think passes through our neural network or our single, right? This is nothing but, what do you think think is? Think is the implementation of. Can anyone see what is happening here with this think function? It's okay. Careful. Look what is happening here. Inside tan h, what is this? It's a function in a function, right? So essentially this is nothing but this operation, right? This operation, this whole operation, right? Inside tan h I have, so you can see this, inside tan h I have a dot product, right? So this is my summation, and my summation is wrapped inside my activation. So this is not nothing but my forward pass. One way of doing my forward pass. Okay, this is what it thinks, right? It thinks and computes whether the thinking is good or not, right? So it thinks, I get an output. After its thinking process is done, I compute an error. So this is nothing but my loss function. As of now I am simply doing actual minus the prediction, right? It's a very simple loss function. And then I will do what? Again, let's go back to our list, right? I have computed the loss, then I have to somehow build my updated weights, right? So if I build my updated weights, this is how, what is the, okay, np dot is a dot product, and numpy dot is a dot product. It's a dot product of, it's a matrix multiplication, right? Yes. So dot is a dot product. So this part basically, this part. How will you do a dot product in NumPy? NP dot dot. That's it. So and in fact, if you see, basically we used to do NP dot dot, but dot here NumPy is already imported, and you can just see dot here. This does a dot product. So what is that a dot product of? Dot product of, if you see, dot product of inputs, whatever you give, with the weights. As of now, the bias term is ignored. It's fine. Basically consider that bias is 0. Okay. But in reality, bias will not be 0. Right? So it is, bias means like it is 0 centered, you can consider like that. But dot essentially means the dot product operation. That is important. Right? So this is exactly what we did. Right? And let's compute our adjustments. This is what is this? This is my dot product of whatever my inputs I've got, comma the error into my tan h, right? So this is nothing but this is actually, if you, in a very simple manner, this is my finding how much I have to adjust. Okay, this is a very oversimplification of my chain rule. This is oversimplification of my, because I have very simple functions too, and there is no going into, so there is a derivative implementation, right? But however, I am actually doing like this to accomplish my backward propagation. Did my forward pass, computed my loss, did my backward propagation, find out how much I have to adjust, and I will do my optimization, where I finally apply this adjustment into my weights. Fundamentally, at its rawest level, this is what's going to happen. Here you might say that, oh, the error is missing a regression term. Fine, when you actually do that, you will realize that you have to add it, but that is what it is. It's a very, very simple program, but it's so effective that, and now if you actually see, create the neural network object or the holder, whatever you want to say, and then the moment you create it, you get a basic synaptic state weights, right? Every time you run it, you will see that you get this. This is my initial synaptic weights, which means my initial weights. I have started with these weights. I have created some sample inputs, some sample outputs, and basically when I train 1,000 times, 10,000 times, and I will get new weights. If you see that after training many times, which is 10,000 times, I have gotten my new weights. And considering a new situation, if this is the case, considering a new situation which is 100, so what is my value? How many samples are we talking about? I have a 1 sample, I have 2 sample, I have 3 sample, I have 4 sample. Okay? So basically I have 4 sample, and if I have a new sample, this will be my value. Okay, that's all it is. Okay? This and this, right? The MNIST one, right? Now if you actually go back to this MNIST, this, by the way, don't worry, I've already forwarded everything and they are working on it. You probably will get it by tomorrow. Okay, max. So this and this should give you an extremely good clarity on how a neural network is formed and built, and what's happening at each level. Because when we go to TensorFlow, you never have to do all those things, by the way, guys. You realize, right? If just one line, TensorFlow handles everything. Okay, and it does it really well, so that you don't have to do anything. Okay. Understood? Any questions? Do we have any questions, folks, on this? Fairly simple. There is an unassisted. Have you downloaded an unassisted notebook? Have anyone downloaded the unassisted notebook? Can you guys run it? I'll give you 10 minutes. Please run it, and maybe one of you can run it. And this is with Sigmoid, by the way. Okay. And try to understand what's happening. I'll give you not, okay, fine. If it is done, then I'll give you 5 minutes. One of you have said done. I think I will give you 5 to 10 minutes maximum. Shubha, we are still in lesson 3. If you actually go to 3.8, please go to 3.8 and download the code. Okay. Means this code is not in, it is just a simple code. How? No, no, no. This is a code to expose to you how a neural network works, right? How a neural network should work. What are the core frameworks, fundamentals of your neural network? Because when we go to TensorFlow, you will not be exposed into so many things. You will simply use the libraries and the APIs that TensorFlow provides, and you will do all these things. The TensorFlow will handle it, right? But if if you do these things and understand it very well, right? Whether today you use TensorFlow or tomorrow you use PyTorch or day after tomorrow you use Teneo, does not matter, Tiano, right? So any framework, there are many frameworks. It's not just TensorFlow, right? There are many computational graph frameworks which are used in machine learning, right? TensorFlow is not the only one. But if you understand this, we have actually gone above and beyond frameworks. This is something that is fundamental for you to understand. What is the activation function used in this particular unassisted IPYNB file? Sigmoid. What is the equation of a sigmoid function? What is the property of a sigmoid function? Can anyone tell? Do we remember what is the property of a sigmoid function? Yeah, sure. Let me just go one more time, okay? It gives probability of, it gives values between 0 and 1, right? Yes. Okay. Suchita, did we understand this part? This notebook? In the first part of here, we have understood this, right? Now we have understood that to build a neural network in any language, in any framework, we need to actually accomplish few things. We have to have the ability to create an object or a holder. We need to be able to add a hidden layer or multiple hidden layers. And each of those layers represents what? There must be a summation function and an aggregation, summation operation and an aggregation operation. So I should be able to add multiple such layers. And the last layer, I should be able to have a summation operation and a special activation operation which should result in probability in case it is classification. So that is my core tenets of a neural network. There is also, you can add this thing, right? You have to add regularization. You can also add dropouts for regularization and so on and so forth, right? You have to choose right loss function. But when you start training, there are 3-4 things that you have to worry about. One is that the forward pass, which does the computation, the loss computation, and then given the loss, you have to using chain rule do back prop. Okay, back prop's objective is to only measure how much the change has to happen via the chain rule definition, which is the partial derivative of this thing, right? Given this, and then the optimizer that we have not yet touched, we have not seen the optimizer yet. Okay, given that, the optimizer will update the change of rates and the loss will finally go down, right? If we understand this bit, then if you have to create a neural network from the scratch with just nothing but NumPy, then how will we want to do it? We will create a class. A class represents a holder, right? We know that the moment we have to create a class, we'll in the class constructor, this is how you write a constructor in Python. You will define some weights. In this case, if you remember, if you see this, I have each example has 3 features, right? So I need to actually have 3 weights to start with, right? So we model. So what has been said here? Please, we are modeling a single neural with 3 input connections, right? So in this case, I need to have 3 weights, right, for every input connection, isn't it? So this is the place where I actually initiate the weights. Again, think about it, in the actual TensorFlow implementation, this will not be the case. It will be a really complicated algorithm called as Havi's initialization or something like that. Hayes initialization, sorry. And it's a very popular algorithm. Okay. because based on the neural network, it has to be pretty complicated. The initialization is very important, but ideally, it's some random number for all the weights, right? We also have to define our, what do we have to define? Our activation function and the derivative of the activation function, right? You can create any shape or form for it, right? Then when you actually do the training, you actually do all those four things. First, do a forward pass. Forward pass is nothing but those summation plus activation operation. This is how you do it, right? Wrap your summation operation inside the activation operation, which is the non-linear part of it. Calculate your loss. You can choose to add regularizers, and then do back propagation to find out how much you have to adjust the weight, but don't just adjust the weight. Back propagation just gets you the metrics to update the weights, and then at the end optimizer will actually update the weight. This is the four fundamental parts of training of a neural network. Once we actually go to TensorFlow, we will see that these concepts are how it is complicated and why it is needed to be the way it is. Because you can imagine, if you are training a million samples and there are 300 million parameters to train, all these operations, by just simply doing dot operation, you will kill your system, right? It has to be in such a way that it supports distributed training, it supports a lot of other things, which is computationally, it has to be computationally intense, not that intensive, right? It should be computationally reasonable on the context. TensorFlow provides you that. But overall, as a whole, what we understood is that nomenclature of what is a neural network is all about. Okay, folks? Are we all clear? Awesome. That is great. That is great. Yeah. Put these things inside your head, because as I said, today TensorFlow, tomorrow some other flow. Okay. And tomorrow PyTorch. The company that you join, the company that might not be using TensorFlow. Then what? You'll have to relearn a framework. But this core concept never changes, right? So that is the reason of understanding this in a way like this. Okay. Awesome. Okay. So we have come to the end of lesson 3. Okay. And when we say that we have come to an end, what did we understood? We have explored neural networks. We have babysit the neural networks in a way that it is framework neutral, and we have got a good understanding, so that we can actually go and tackle TensorFlow and its own beast, right? TensorFlow framework is fairly heavy, and there's a lot of options and a lot of things, and it abstracts information to you. But given a problem statement, given there is a problem that you have to debug, you should be able to in a position to fix it, right? We have seen that what is a weight to a loss. That loss is nothing but a view of a weight, right? And everything else is just weights and biases, not only weights, right? We have understood that why forward pass is important and backward pass, right? What happens in forward pass, and we have understood, I think, from an intuition standpoint, what happened in backward pass as well. And we've looked at that chain rules and its usage in backward propagation, and how important it is. This is a extremely important algorithm, introduced by Jeff Hinton. I don't think he invented it, but he's the one who actually made the algorithm in such a way that it can be used in really large networks. Okay, there's some significant amount of improvement he did, and we've also seen that, like any other machine learning algorithm, neural networks are also very, very prone to overfitting, right? And there's generally multiple approaches similar to classical machine learning. We can use L1 and L2 regularizations as well as L1, L2 together. Okay, and however, we can also look at adding layers like dropout layers, which try to allow you to generalize things. Okay. Awesome. This is great work. I think we have done very good. Let's do one thing. Let's let's start our next session, next lesson essentially, and let's have a plan around it. That what are we going to do in lesson 4, so that maybe we can discuss some of those few slides and reach to a point. We still have half an hour left. Maybe what we can do is like we can do for 20 minutes, and more questions might come. Does that work for you guys? Or do you have any other questions on neural network? Any questions? Any fundamental basic questions? Anything that I have missed? Anything that we want to repeat? Let me just actually stop sharing and for a second, and before that, let me know if you have any specific questions. Meanwhile, let me open my lesson 4 document in presentation. Okay. I can show definitely. I have shared it. I have just shared Jan Goodfellow's, right, a deep learning book. It's a very famous book. Okay, it's a very, very famous book. Okay. Can anyone reshare the link, please? Yeah. So this is a very popular book, by the way. No worries. Okay, guys, I have a short update. There seems to be some more technical issues, and the files might take a little longer to reach you. But don't worry, Simply Learn, IT support will definitely put it before your next session will start. Okay, I have forwarded everything, so don't worry about it. We can always come back to them, come back to this again and again. We have time, so there's nothing is going away. We can always come back to any concepts that we want. Okay. Yeah, so it will definitely be shared before next session.
Yeah, as Sandeepan has said, we are working on it, and the files will soon reach you. We are trying our best to share with you as soon as possible, and it will be definitely available for you before the next session for sure. Thank you everyone for the cooperation.
So the MNIST test CSV, okay, I have shared the link yesterday. Let me reshare it one more time, okay? It's actually a very public data set. You can get it from Kaggle as well, but let me send it from where I have downloaded, okay? And this is the link, okay? This is again an open source link. I will not share a single link which is not open source or which is behind a paywall or needs some sort of IP, okay? It's and so this is you can say this is basically from a Python course. Okay? So you can download this. In fact, MNIST is also available in Keras implementation, or even in sklearn also we have MNIST. Okay, the data is already available. So if you actually go there, if you actually go to this Python edu data.mnist, right? This page. So you want the test, is it? One second. I got what you're saying. Okay. Okay. So this is MNIST. Can you also look at this? This is public domain. Okay, so you can look at this as well. Okay. Okay. So this is a Kaggle, but this is also says that this is the license is in public domain, so it's not someone's data. Okay. So original data set is so yesterday, if you remember, you can actually take it from here as well. Jan LeCun's public page. Okay. So this is also a place where you can get MNIST examples. Okay, Shubha, what is your problem? Where can I find the codes? As in, the code, I have shared you the codes, right? The examples of the code. I've sent you the location, right? So yeah, that is the code itself. That is the IPYNB file itself. It's already coded. Okay. Let's spend some time on our next um, topic, which is um, nothing but this is our lesson 4 that is we're starting. Okay, guys. Let me also open the chat window. Okay. Right. So we will be starting our lesson 4, and we'll today we'll just understand what is that we have in mind, and this is, and then we'll see that how we can capitalize on this, right? So this is our lesson 4. Let's first of all look at what are the various lesson plans that we have. Okay, let's do one thing. Let us go to self-learning page. Okay, if you go to self-learning page, open the lesson 4. Okay, deep neural network and tools. What does it says? It says that this is a, essentially 13 things that we have to do except the knowledge checks, right? So we will discuss the deep neural YN applications. We have understood this very, very well. We will skim through this very quickly. We will design a deep neural network, okay? And we have designed actually a deep neural network very well, okay? But we will also go through this, and we are going deep now, okay? In this case, as the lessons progress, we will go deep into these things, right? 4.3 is that how do we choose our loss function? There was a question that how do we know which is the best loss function? This should help us, this particular chapter in this particular lesson 4 should help us to understand, right? Then we will actually focus on what are the various tools that we have for deep learning models, right? We go to the first framework that we understand, that is at least noted here, which is called as Keras. Okay, and there is this confusion between what is Keras, what is TensorFlow, what is TF-Learn. We will actually deal with it. In fact, the whole of lesson 4 is all about, mostly about Keras and TensorFlow and the framework angle of it. So we are now shying away from building a neural network by hand, and now we are trying to produce production ready code using TensorFlow or Keras or TF-Learn, either one of that. Okay, and we'll explain why there are three things. Just like any other things in machine learning or anything in the world, we have opulence of frameworks here. Okay, there are a lot of frameworks. Okay, and then it is better to know multiples of them, and that's where we'll make you these things. 4.6 is a demo set. I would highly encourage all of you right now to download this data. If you have already have access to 4.6, if you can see it, please download 4.6 Jupyter Notebook and upload to your practice labs. In fact, even if you don't do it now, please do it before tomorrow, before the class starts, right? And create a folder-like structure here in such a way that it's easier for you to handle. This Jupyter Lab notebook stays for 15-20 days if on inactivity. If you continuously activate, you can use it for a longer duration as well. Okay. So this is, please download it. 4.6 is your assisted practice. We will go through this tomorrow. Okay. And again, we have MNIST dataset. So you already have the CSV files. If the CSV file is needed, we will use it. But I think we don't need it because we will use the Keras given MNIST dataset. Okay. So when I start the class or the practice session tomorrow, I would not like to ideally hear that this is running, this is not running, that is not running. So please be ready with this and upload it, right? We have gone through this today. After this, we will actually start the TensorFlow and its ecosystem of it. Remember that, okay? That is important because we have to understand this framework, right? This is, after all, deep learning with Keras and TensorFlow, right? So we will actually understand the ecosystem of TensorFlow. We will actually do a we will do our first neural network model using the same problem statement on MNIST. Okay, using MNIST, and but this time we will not babysit it. We will use TensorFlow. Right. The last one we used Keras. Right. In 4.6 we have used Keras. In 4.8 we will use TensorFlow. And you might ask, oh, I thought that we will only learn one framework. You will actually learn one framework, but we will see that what is the difference between Keras and TensorFlow. It is just, Keras is little easy. Keras internally uses any sort of backend. It can use TensorFlow also as a backend. TensorFlow is more like an operating system. Okay, Keras is something like an API. You can think like that. Though now after TensorFlow 2.0, everything is inside. Okay. Earlier, TensorFlow Keras used to come as a separate package. By the way, the guy who actually created Keras, his name is Francis. I don't know how to say, pronounce the last word. Okay, so Francis Charlotte, right? He's a very famous researcher. You should, so you should learn about all those things. Okay, people who have actually contributed great deal of things, right? And his book on deep learning with Python is also very popular, by the way, guys. Okay, very, very popular. Only thing is that you have to, this is something that you should buy a paper copy. I would strongly suggest you should buy a paper copy, right? Then after 4.8, we will actually go to another framework called as TF-Learn. Okay, this is again one more layer on top of TensorFlow, like Keras. It promises to be little bit easier directly than using TensorFlow. Okay, just like Keras. We will look one more framework called as PyTorch. You can ask, why are we learning so many frameworks? Because it is good to know. It is good to know which works best, right? There is not one size fits all. So, but that is what we will actually focus on. And I think that tomorrow's session should be a self-sustained session, and we should be able to spend most of our day by finishing all of this together. So I would highly encourage to download all these assisted notebooks and keep yourself ready for that matter, right? Okay, so deep learning and tool is all about the frameworks that we will use to train a deep learning network. If you use Google Colab, can you explain how to use GPU? So if you use Google Colab has, so the thing is that first of all, as part of this training as part of this mentoring and teaching session, you should not use Google Colab. You should always use Practice Lab. Okay, but if you really want to use Google Colab on your own time, okay, there are two things that you have to do. Okay, you have to go to there's a way you can go and add GPU to your VM. Once you add GPU to your VM, you have to use TensorFlow distributed training. Okay, there is something called as TensorFlow's distributed training. That is what you have to use. Okay, just simply adding a GPU to your VM, it will not run the code in GPU. Okay, because the instruction set has to move from CPU to GPU. That is done by something called as TensorFlow's distributed training. In fact, if you are interested, remind me tomorrow. I will give you a link. It's a very simple link. You can just see the code and how it is done. Just type distributed training in TensorFlow, and you will see that you have to use a strategy pattern. Okay, you can now, why GPU? You can go to TPU also. Okay, Google Colab gives you TPU as well. But while we are in the class, and I will highly encourage you to use Practice Labs, for the reason that it's a common ground from all of us. Okay, that's what it is. I think that let's spend our next 20 minutes discussing if you have any other questions. Maybe anything about, rather than starting the new lesson, I think we should do the lesson. Let's keep the lesson for tomorrow, and let's discuss whatever we have to discuss. Any other question? Any other? And if you want to review this one more thing, I think let's do that, so that we are very, very clear on what we want to do. Okay. Shall we do only Q&A? I think we should do only Q&A. My suggestion is that let's do only Q&A. But I leave it to you guys what you want to do, spend next 15 minutes on. Mathematical part of differential equation. Um, yeah, I think we should do that. We will do that. We will have time. See, I'll tell you. Okay, come here. So now in lesson 4 we have this, right? I can, you can see my screen, right? You see this? Lesson 5 we have optimization algorithm, right? And we have other things, right? All these things. So in one of those things we can take the mathematical. So mathematical part of differential equation, what I'll do is like I can create a small I want to create in a way which is consumable by everyone, people who are expert as well as people who are at some level. So let me create something, and I'll also take permission from Great Learning teaching team. And this is a good question. This is something that you should know, because without differential equation it is very impossible to understand. But I can build something for it. We can definitely target for lesson 5. We have time. Don't worry about it. Yeah, I'll keep that in mind. How to choose activation function? Okay, how to choose activation function? Before that, let's how to choose activation function. Okay, please share. I have shared it already. Okay, what I said is that I have shared it. So it will come to you, Shiv Shankar. It will come to you via the support team. Okay, LMS, they will send it, right? Learning success LSMs will send it to you. I have already sent that notes. How to choose activation functions? In fact, if you look at the activation, what okay, let's 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 look at this piece, right? What is that you have to? What is that the activation functions are actually doing? Can you think what is the exact thing the activation functions that they are doing? At its lowest level, what is it doing? It is trying to do. It's not adding any features. Definitely not. It is not definitely. It's somewhat doing neuron activate, but okay, what do you mean by neuron activate? You are there. So one thing is for sure, it is not adding any features. It's not intentional. It is transforming, right? Basically, what it is trying to do, what do you want it to do? The what you want it to do is two things, right? You have to transform it. Perfect. In a mechanism, so that each of this neuron, represents that they are important or they are not important, right? In each of this neuron they are important. So the output of this neuron, if it is big, then can I assume that this particular neuron in this whole set of 9 neurons, 9 plus 2, 11 neurons, is probably the important neuron, right? For whatever reason, whatever this neuron is seeing, his output will tell it, right? He must have seen a very important piece part of data, and that is what the output of this activation function is. Summation, he has done whatever it is, but activation ensures that it gives you a scalar value, right? Or basically one value from this in this particular neuron, right? So now the value that it outputs should represent in such a way that it's, first of all, it we have to ensure that it is not very large in both the sense. Like it cannot be like minus 15,000. I'm not saying it cannot. Why am I saying? Because if you have a very large value, these are all mathematical operations. You are doing multiplication and then you are doing addition, right? Though there is no square, but think about it. If you have a really large value, your 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 end value will also be extremely large, right? So we cannot allow it to go really big. So we would want it to be in between certain range as well, right? First of all, these values must represent some sort of importance of each of these neurons. If this neuron is so important, if this layer of the neuron is so important, this neuron should be the highest one amongst all the 11, at least in this pass. Maybe it is seeing something really good, right? Maybe it is able to identify that particular person's face itself, right? So, so that is what it basically represents, right? It basically gives you a number. So what you want is some sort of representational number which is not that very high, right? And based on the position of the layer, suppose if you're in the last layer you want probability estimates. In the middle layers, you don't want anything between 0 and 1. Okay, sorry, you might or might not, but it's okay if it is not point. It's 1 and 2 and 3 are also fine, but it doesn't have to be too big, right? Then you also have to ensure that the output cannot be zero. If the output of these neurons are zero, then while you are doing backward propagation, what happens? It's gonna be very difficult for you to compute the gradient, right? Because gradient of zero is like, it will end up like this, right? If you apply chain rule on a zero, and everything will be zero. So gradient of, if when the moment there is a gradient zero, what will happen? The learning stops. Your weights will remain same, and then the learning will stop. So given these three parameters is sufficient for you to judge whether a activation function is good or bad. If you use sigmoid, you will see that anything beyond 2-3 layers it's useless, because it will create this problem of vanishing gradient. Okay, that your your gradients or your weights will be so less, or the output of this thing is so less that you have nothing to do, right? It's going to be very difficult, right? ReLU is, after a lot of effort, ReLU people have found out that it was working pretty well for a large set of problems, extremely large set of problems, right? Right. You also don't want 0 on 1, right? So yeah, I think univocally you have seen that in vision problems, in RL problems, in language problems, ReLU or some version of ReLU is working really well. And again, right, if the more number of layers increases, right, this problem of vanishing gradient is acute then. You have to understand, right, when you do back propagation, the biggest problem is this vanishing gradient or exploding gradient, both. If it is extremely too large, what will happen? At some point the number is so large, you might actually spill over that floating point operation, right? Or if it is zero, you stop learning. Both are really bad, right? If your learning rate is too small, you are taking extremely large amount of time to converge. So these are real problems if you have a big network. So ReLU has been seen to generally work in many cases, and there are a lot of different versions of ReLU. I said, right, something called as leaky ReLU. So basically, if you see what is ReLU, ReLU is a very simple function. So what it says is that it's like this, right? So anything above this is 0, make it 0, and this is infinite. So the only problem is that this has no bound. On this side, you don't have any bound. So if you pass it via ReLU, it is possible that it might give you 10,000 or 10 lakhs. It's also possible, but it will never give anything below 0. So at a very, very large network level, if you have many, many layers, 1,000, 2,000 layers, it is possible that ReLU might actually also explode. So what they have done is that, so they have ensured that just that there is no, it can explode, and in fact, in this side, it can vanish as well, right? If you have, you continuously getting this side of the equation from ReLU, then all the weights are 0. So what they have done is that they have created a new version of ReLU. What it does is something like this. Okay, and the one side is this and the other side is little bit high. It's not 0. And this degree you can control that, how much degree it is, right? So generally, by default, if you have to use, go with ReLU, right? TensorFlow does not make a default activation function for you. You have to give the activation function. What TensorFlow also does is that it, however, gives you a default algorithm for weight initialization, okay, which is that Hayes initializer. Okay, he was also a scientist from Google, I think, if I'm not wrong. So that is what it is. So very deep question, very important question, but we will see that. Okay, we will see all those things, right? What else? So, but just try to understand that the core concepts. I think more you understand it, more better. Is it possible to share the notes? Notes are already being given. I know you are seeing a lot of text here, but I think it will be good to save time while revision. Absolutely, absolutely, agree. Can you use different activation function for different layer? Absolutely, absolutely, yeah. But can you use? Okay, yes, per different layer. Yes, yeah. Can you? Yeah, you definitely, because if you remember what was So this is what it is, right? This is how my pseudocode looks like. What was stopping me to use here sigmoid or tan H? Nothing, right? I could have used it, right? And they suppose E relu or sorry leaky relu. Right? I can easily do this, right? But what I cannot do is, I cannot change per neuron level in a layer. Okay. That is correct. So as in regression, we've got so if you actually look at it, right? So this is what we saw. So this was our output of my, if I have the same 4x and 1, so what will be my linear equation? M1 x1 plus M2 x2 plus M3 x3 plus C, right? Because I have 4 x's, right? This is my equation. What is my weights here? My weights are what is my coefficients? M1, M2, M3, M4 and C, right? So this is in a generic term, you can also call them as weights. Why? Because they represent how important x1 is. M1 represents how important x1 is. M2 represents how important x2 is, and so on and so forth, right? Isn't it this each weights also represents that, right? Remember, each of these lines in the weights also represents exactly that. If a weight is less, if this weight is high than this weight, that means that you are trying to in a way say that this neuron is important than this neuron, isn't it? So in a way, what you see is that these coefficients in a generically they are also called as weights, and C is nothing but bias, right? So generically everything is weights and biases, even in your regression or your classical machine learning problems. Why it is coefficient and slope and sorry intercept? Because you think from a line perspective. If you think from a machine learning point of view, everything is weights and biases. And ultimately it's going to be a bunch of weights, billions of weights, millions of weights, and that is something that you have to update and keep on maintaining it, and so on and so forth, right? That is what it is. A model is nothing but a bunch of weights, a bunch of numbers, lots of big huge numbers. That's it. Large bunch of numbers. And what are those numbers? This nothing but these weights and biases. That's it. All good questions. Awesome. Good session. I liked it. We've asked a lot of questions. We've gone through a very important mechanism of visualizing a neural network's function of functions. We've actually differentiated it to some extent, and what we'll do is like we'll look at the mathematical angle of it, and let that be. Let me do that. Let me create that. I'll ask learner success managers as well, but I think I should create it for you guys. Any other questions before we wrap up? That's a great question actually. When do you decide we should actually go with NN instead of ML? Well, NN is a part of ML itself. I hope that is clear now. So what you're asking is that how do we decide I should use a classical machine learning problem? If you have very simple, right? In a way that if you have a complicated nonlinear problem with extremely large number of data, right? Go with neural network. You have really lot of data, right? Go with neural network. If you're trying to solve vision problem, go with neural net. If you're trying to solve language problem, okay. Nowadays these problems are very first-hand kind of thing, right? Directly go with neural networks. If you are trying to solve unstructured data sets, or for that matter, this thing, right? Tabular data set, right? If you are talking about tabular data, and then but you have really large amount of data, right? Like I'm talking about in millions, and maybe in billions. I think neural network is a good way to fit it because the quantum of data we might itself make the classical machine learning model. Like if you take SVM will work very well to some extent because the data is very big. Okay? I think when the data is improper, okay, definition of what do you mean by improper? Are you talking about imbalanced data? Is it imbalance when we have class imbalance, right? Is it necessary to learn big data for deep learning? Okay, big data technologies is what is big data technology? Is the mechanism how do you extract big data from different source system, right? It's so typically machine learning engineers don't worry about how the data is coming. Okay, there's a different class of problems. You have PySpark, you have Hadoop infrastructure, you have big data infrastructure to deal with that. Typically, deep learning or deep learning ML engineers, once the data is there, what you do with the data is a question, right? So deep learning comes in that part. So there's two different problem statements, but will it harm you to know what is big data? Probably not, but they don't collide with each other. But it is also important for you to know from the where the data is coming, right? If you so it's not necessary for sure, but knowing is not a harm. If you know something, it's always better to know, right? But as long as you understand that what the two concepts is fine. However, the big data, by virtue, I understood that you are talking about from where the data is coming, right? Like via Hadoop systems, large jobs, BigQuery, so on and so forth, right? Or the ETL systems, right? Cloud-ready ETL systems, and so on and so forth, right? Deep learning is once the data is there, what do you do with it, right? So in all of these things, we will actually talk about the data is already there, and then we do something about it, right? That's what it is. However, what you also you might have to know is that as a data scientist or a machine learning engineer, how do you represent this really large big data into visualizations, right? If you have millions of features, you need to compress into two, three parameters or features and then present in a visualization, right? That requires a certain amount of skills, but that is from a visualization standpoint, not from a data fetching standpoint. Okay. Okay, sir. I think let's call it a day, and let's come tomorrow. Let's come prepared, by the way. And tomorrow, let's have all our stuffs in our practice labs, and hopefully you'll get the materials before tomorrow. I hope today's session was good. We have gone through pretty detail of it, and tomorrow will be a interesting day as well. Okay, if there is no other questions, thanks a lot, folks. Is there any other questions? Do you want to ask any other questions? Thank you. Thanks a lot. I have taken all the things. We'll see tomorrow. Okay. Thank you. Thank you very much.
Thank you for the wonderful session, Sandeepan, and thank you everyone for your time. So there's a feedback survey from in your browser where you can submit your feedback. If you liked our session, please rate us a 5, and for anything less than 5, please share your comments to help us understand what went wrong, so it will help us improve in the upcoming sessions. Once again, thank you everyone. Have a great day, and bye. Okay, so everyone who hasn't yet received the file, please drop it in the chat box. So we will keep a note of it, and we will be sharing the files with you soon. And regarding the project, the deadline of the project is 15 days from the last class of this session. And I have also seen other queries regarding the project submission and the technical details and guidance. So you can contact us in the LMS where every request and query of you will be handled with our expert team. So please feel to share all your queries and doubts with us. We are always there and happy to help you. Thank you everyone for your time. It's 15 days, Gautami. So all files which are shared by our trainer will be shared with you via mails. And please do not share any files amongst you personally, as it may result in further problems if it is not handled properly. So that's the reason why we are saying that we will be sharing all files with you on time. So are there any further queries which are to be addressed? So Arshita, regarding live classes on data science with Python in April, we have to confirm it with our team as it is a different course. I will be reaching out to you, or any other LFM will be reaching out to you regarding the confirmation of that. Have you created a ticket for that? Okay, Ashita, I will keep a note of it. Thank you so much for contacting us regarding your query. And for any query, please feel free to contact us even during the session or after the session. You can take your time and put it in the chat box, and we will take it up from there. Okay, Bhuvanesh, yeah, I have also noted your query that you have used your official email ID for registering the course. Okay, so Bhuvanesh, I think you have to add your mail ID which you intend to receive the file. Okay, so that means how to raise a ticket. Okay, everyone. So I'm receiving multiple queries at the time. So currently I'm noting every one of your queries which are in the chat box, and we will reach out to you soon regarding all the solutions. Okay, Aishwarya Satpure has also haven't yet received the files. Okay, Aishwarya, I have noted it as well. Okay, team. So regarding the help with project, please raise a ticket in our LMS, and our technical team uh, will take it up from there, and they will help you in resolving it as